Hallo.
Hallo.
Sorry, Carsten, ich habe es versucht mit dem GatherTown, aber ich hatte vergessen, das Mikro freizuschalten. So konnte ich nichts sagen und auch nichts verstehen.
Und auch nichts hören. Nichts Wichtiges hören.
Aber das schaffe ich auch. Sorry, Carsten, ich habe es versucht mit dem GatherTown, aber ich hatte vergessen, das Mikro.
Okay, there was some feedback.
No, sorry, it was the YouTube stream. I normally get that. Just checking that it works.
Okay, I think we will start soon, but it's not yet 2 p.m. We will start at 2 p.m.
Well, good morning, Kirsten.
Good morning, Kevin. Actually, afternoon here.
Yeah, I meant to say yesterday, I'm sure glad you guys didn't change your clocks last weekend.
Yeah.
Just barely make it up for this, as it is.
What's the time in Waterloo?
Well, it's 9 o'clock now, but
yeah, it's okay, right?
Well, it's fine, but it still feels like 8 o'clock last week. So our clocks changed on the weekend. Oh.
Okay, hi, Dor.
Hi, everyone.
Hello.
Good morning.
Good afternoon to you.
Okay, so almost 2.
Good night.
So then, welcome again to our workshop, Eddy-Wave workshop. And yeah, I think we just start right now with Fraser. Actually, on the plan, there was David Marshall now, one of our Mercator fellows, but there's a problem. Sadly, David has, or David's father actually recently died, so, and he's not prepared to give, to work or to give talks at the moment, he told us. So he decided to let the stage to Fraser, who did the work anyway. And we are happy that Fraser is presenting his work and not the professor presenting his work. So Fraser, please go ahead, share your screen and start your talk. So is there a problem? I cannot see anything. Or is it just me that don't see?
I think Fraser had another freeze of the screen. I think he actually has to.
Maybe we'll try to get in again. Oh, I cannot. Can you see him on the list?
No, he's not in right now.
Okay, just wait for a minute.
Give him a second.
So then internet broke down in the UK. Okay.
Maybe not everywhere in the UK, maybe it's just Fraser's internet.
Okay, he's coming in now. Fraser, are you there?
Oh, hi there. Yeah, sorry, Zoom just crashed for me.
I don't know if there's an issue with internet. You could also turn off your camera when you speak, so maybe it's
yeah, that's a good idea.
That way, yeah.
Okay.
Okay.
Okay. Then please start sharing.
Okay. Sorry about that. Hi there. So I'm Fraser Goldsworth. I'm going to be talking today about work that I've been doing with Dave Marshall and Helen Johnson at the University of Oxford, looking at symmetric instability, which is a type of sub-mesoscale instability in cross-equatorial western boundary currents. And in particular, the talk's going to focus on western boundary currents similar to the North Brazil current, which is the western boundary current which crosses the equator off the coast of Brazil in the tropical Atlantic. So we're going to zoom in a moment to a really small scale and the tropical Atlantic. But before we do that, I think it's really helpful to think about the bigger picture and think about the global scale circulations we see in the Atlantic. And in particular, I think it's important that we kind of motivate this work by thinking about the global conveyor, which is the Atlantic meridional overturning circulation. In the surface, we have this northward flowing current, which is relatively, or which brings with it warm water, carbon, various other climatically important traces across the equator before flowing northwards to the poles. Depositing some of the heat and some of the heat which it has as it goes, and that really influences the climate here in Western Europe. At the poles, this water gets cooled, becomes denser and saltier, and we get this return flow in the form of a deep western boundary current. And this too has a cross-equatorial component, and this global scale current kind of, I guess, drives some of the cross-equatorial flow we see in the Atlantic. And we're interested in the sub-mesoscale because instability at the sub-mesoscale, at the equator in particular, could lead to maybe could, in theory, lead to a bottleneck, perhaps in the AMOC. So if we if we restrict the amount of fluid able to cross the equator here, that may have impacts further along this current. So that's kind of a motivation for this work. It's to understand the effect of whether sub-mesoscale instability has the capacity to be able to do this. We're now going to zoom in a little bit. So this on the right shows a kind of this diagrammatic representation of the currents in the tropical Atlantic. So in the surface, we have the North Brazil current, which is a really important cross-equatorial component, or a lot of the water which forms the AMOC crosses the equator in the North Brazil current, this western boundary current. It's a relatively intense western boundary current. We get speeds of about 80 centimeters per second in places, and relatively narrow, so less than 100 kilometers in width. So this crosses the equator around 6 degrees north. It retroflects. Sometimes this latitude of retroflection is further north or further south. It kind of depends largely on the atmospheric forcing. And if the retroflection is particularly strong, sometimes we get these eddies pinch off, which are called the North Brazil current rings. And these transport a lot of southern hemisphere water, or waters which originated in the southern hemisphere, away from further away from the equator, still towards the Caribbean. These are really strong anticyclonic eddies, about 200 kilometers in diameter, and we get a few of those forming each year. And below this surface current, we have the deep western boundary current, which crosses the equator as well. This is much slower, speeds of around 8 centimeters per second, but sometimes a bit higher, maybe getting as high as 20 centimeters per second at its core. But generally a much slower western boundary current, which flows along the bottom. But for the purpose of this talk, a lot of what I'm going to show you, so I'm going to show you some numerical simulations, and I'm going to show you some results of some linear stability analysis. A lot of that is going to relate to the North Brazil current and what we see in that. So this talk is about symmetric instability. I'm going to in cross-equatorial western boundary currents, and I'm going to explain now why we've chosen symmetric instability in particular as a candidate for, or as an instability which might be occurring in cross-equatorial flows. Symmetric instability is really linked really closely with the idea of potential vorticity. So I think it's important we talk about this first. So potential vorticity is a quantity in the ocean is materially conserved. The Ertel potential vorticity given by this equation here. So we have a planetary vorticity component. So that's contribution to the vorticity arising from the Earth's rotation. A relative vorticity component arising from the rotation of the fluid relative to the surface of the Earth. And finally, this stretching and baroclinic term at the end. And what the material conservation of potential vorticity means is that if we follow a fluid parcel around, we expect its potential vorticity to not change in time. Symmetric instability is related to potential vorticity via its instability criteria. So a necessary condition for symmetric instability to occur is that the planetary vorticity and the potential vorticity of a fluid have opposite signs. And we can do a bit of a thought experiment to understand why you might expect to see symmetric instability excited in cross-equatorial flows. So if we start off in the southern hemisphere, where the planetary vorticity is negative, for the fluid to be stable to symmetric instability, the potential vorticity must also be negative. We can then imagine adiabatically advecting this fluid parcel across the equator. We'd expect its potential vorticity to remain negative, but at the equator there is a change in sign of a planetary vorticity. So all of a sudden we have this situation where Q is less than 0, but F, the planetary vorticity, is greater than 0. And so this instability criteria is met. And we conclude that if a fluid is initially stable, or a fluid parcel is initially stable to symmetric instability in the southern hemisphere, it will not be stable to symmetric instability in the northern hemisphere. And the same applies to flows going from the northern hemisphere to the southern hemisphere. But that's not the end of the story. We also need the growth rate of the instability to be appreciably large to actually be able to see the effects of symmetric instability in a cross-equatorial flow. And the growth rate we can approximate. So if we neglect viscosity, the growth rate is given by the square root of this quantity here. So the absolute vorticity multiplied by the planetary vorticity. Close to the equator, the planetary vorticity is very small. And so what this means is that we need, for the growth rate to be large, a large relative vorticity. And one place we see this is in western boundary currents. So this is why we expect we might see symmetric instability in cross-equatorial western boundary currents. What does symmetric instability look like then? So to go about answering this question, the first thing we did was we looked at performing a linear stability analysis on a meridional jet, which was symmetric in a meridional direction, and had, I guess, a velocity profile and a density profile similar to what we see in the North Brazil current. And what we found from the linear stability analysis is that we get, in regions of negative PV, we generate stacked overturning cells as a result of the excitement of symmetric instability. So this plot here on the right shows the overturning stream function as a function of depth and longitude in such a current. And yeah, we can see these stacked overturning cells alternating in the sense of their rotation. I've also shown the absolute vorticity across the width of the domain that we used in this linear stability analysis. And you can see that there's this region here where the absolute vorticity is negative, and this is where these overturning cells are really strongly localized to. And finally, I should say, so the vertical extent of these overturning cells is set by the vertical viscosity. And this raises some really interesting questions about symmetric instability and how it might manifest itself in models, because in models we use artificially inflated eddy viscosities. So there's some interesting questions there to be answered, but I won't go into too much more detail about that here, other than to say that if we also find that if we set the vertical viscosity to be sufficiently high, we can actually completely we can suppress symmetric instability and basically get rid of it, which is useful in numerical models, as I'll show you in a few slides' time. So moving on from this linear stability analysis, which is kind of gives us this analytical prediction, if you like, of what happens in a symmetrically unstable current. We then performed some numerical models. We then performed some numerical simulations using a two-dimensional model of a surface intensified western boundary current, again with a density profile and a velocity profile similar to that we see in the North Brazil current. And we cite the domain at about 4 degrees north. And what we see is, so here I've plotted again, this is the stream function from the numerical model as a function of depth and longitude at 3 different times, so after a week, 2 weeks, and 3 weeks. And again, we see the development of these stacked overturning cells, particularly clearly after 2 weeks even. This is good because it kind of verifies that the linear stability analysis was on the right track with its predictions. But what we can also do is we can look at how the potential vorticity in the numerical model varies over time. And that's what's shown in this lower panel. So we have this initially, this blue region, or this faint blue region, which corresponds to negative potential vorticity. And this vorticity we expect to lead to symmetric instability. We can then see after about 2 weeks the effect of the overturning cells. So the overturning cells are vecting waters with positive and negative potential vorticity around the domain and causing mixing. So it mixes the potential vorticity laterally and vertically. And what we end up with is after around 3 weeks, this marginally stable potential vorticity configuration. By marginally stable, I mean that the potential vorticity is set to approximately 0. And so from this, we can conclude that symmetric instability is really quite efficient at getting rid of these potential vorticity anomalies. So this negative PV in the Northern Hemisphere. And so we might expect to see this in more realistic models too, or maybe even in nature itself. So the 2D simulations make a lot of simplifications, to go a step further, we started looking at some 3-dimensional, very idealized numerical simulations of the tropical Atlantic. And what the 3-dimensional simulations give us, but the 2-dimensional ones don't, is a meridional coordinate. So in the 2-dimensional simulations, there was no meridional variation at all, so there were no eddies. Whereas we know, I mean, we saw a few slides back the North Brazil current rings of these huge eddies which form after the equator. So any model of cross-equatorial flow should really be able to explain something about their behavior. We also, in the 2-dimensional model, were situated on an F-plane, so we had no meridional variation of planetary vorticity, which is what we thought in the first place might be leading to symmetric instability in cross-equatorial flows. So 3-dimensional model gives us these two things. These models, as I say, are still very idealized though, so we take a lot of liberties with the approximations we make. We approximate Brazil as a straight line, which it most certainly is not. We also neglect all topography, so we have a flat bottom at about 1,500 meters deep. And at the north and south, we have open boundaries in our model because we can't possibly model the whole of the Atlantic at the resolution required to resolve symmetric instability. So this plot on the right shows the potential vorticity we use to initialize our three-dimensional models with at a depth of 50 meters, and we have the x-coordinate and y-coordinate here. And we expect negative potential vorticity, so blue parts, to become symmetrically unstable in the Northern Hemisphere. So now it should be coming to life, and you should be able to see how the potential vorticity field at 50 meters develops. So now, after about 3 weeks, most of the potential vorticity in the Northern Hemisphere has originated from the Southern Hemisphere, and we see close to the equator, we get these eddies developing, these large anticyclonic eddies start to spin up. And these eddies kind of seem to pool and concentrate negative potential vorticity. So here's an eddy here. This seems to be a fairly robust feature of cross-equatorial flow, and it's discussed at length in studies by Edwards and Pedlowski in 1998 and Moles Goes et al. In 2009, write extensively about these eddies. But we're seeing something else. So if we focus on the cause of these eddies, where we're concentrating all this negative potential vorticity, which we think is symmetrically unstable, we see these sub-mesoscale features start to develop. So here we see kind of this these blobs of the large blob of negative PV breaks up into a flurry of positive and negative PV, and eventually we're left with eddies which look something like this, which have a marginally stable PV configuration. And this, we think, is the result of symmetric instability. And this is really quite exciting, especially the fact that it seems to be so vigorous and so effective at neutralizing the anomalous PV. So to try and understand what's going on, and try and come up with something which we try to come up with some potential diagnostics for looking at whether symmetric instability is occurring in other models. And one of the diagnostics we proposed was by looking at the correlations between potential vorticity and relative vorticity as a function of latitude. And I'll talk through what we're seeing here. So just north of the equator, so south of so from around 200 kilometers north of the equator and further south, we see here, this is a plot of a relative vorticity and a potential vorticity at the same instant. We see that the sign of a relative vorticity and the sign of a potential vorticity match. And this means that the relative vorticity dominates the potential vorticity balance. If so according to the conservation of potential vorticity, as we move these fluid parcels further north, we'd expect as we're reducing the planetary vorticity, we'd expect to increase the magnitude of the relative vorticity, and we'd expect this relationship to carry on holding. But if we look around 1,000 kilometers north, we see this isn't the case. So here we have a big pool of negative relative vorticity fluid, whereas its potential vorticity is now 0. And this means that the planetary vorticity is dominating the vorticity balance. So something has changed in between. And we think that this is symmetric instability, which is altering the potential vorticity balance. And we can see this eddy here seems to be undergoing the process. It seems to be symmetrically unstable and undergoing the process. Undergoing those unstable motions. We can try and be more concrete about this, and then what we've done is we've plotted the correlation between the potential vorticity and the relative vorticity as a function of latitude. So we take the potential vorticity and the relative vorticity pairs at each latitude and over time, and we calculate the correlation. And we do this for basically a no-slip model run, which is like the one we just saw, and also one with a free-slip lateral boundary condition, just to see the test for sensitivity. And we see around 250 kilometers north, we get this, which is around where we see symmetric instability starting to come into play, this sudden drop in correlation. So that's quite interesting. And we can be sure that it's not the eddies which are causing this, because we're able to run the same simulations, but with a massively inflated vertical viscosity, which is able to shut down symmetric instability. And in those runs, we don't see any drop at all, or barely any. So these are what these dotted lines show. We see barely any drop in the correlation, suggesting that the drop in correlation is in fact a result of the symmetric instability, and not the eddies we're seeing. So another diagnostic we looked at was the power spectra of the vertical kinetic energy. And this was inspired by Elizabeth Jankowski and Sonia Legg in a 2019 paper, suggested that symmetric instability had a fingerprint in the vertical, in the power spectra of the vertical kinetic energy. So what we've done here is we've selected an area just north of the equator. It's from around 250 kilometers north to 750 kilometers north, where we think we're seeing symmetric instability. And then what we're doing is we're calculating the vertical kinetic energy at a depth of 50 meters and taking the Fourier transform. And we've plotted we've plotted this at weekly intervals, so after 1 week, 2 weeks, 3 weeks, etc. And we've done this for 4 different models. So the standard 3-dimensional model is that model which we've just seen a video of. And the standard 2-dimensional model is kind of the 2-dimensional model we saw at the start with those snapshots. And what we see is over time we get a lifting and a flattening of the power spectral density. So this here is the power spectral density, and the x-coordinate is the wavelength. And so we see a flattening of these lines. We've also, again, we can run these models with a really high vertical viscosity, which is able to suppress the symmetric instability. In the case of a viscous 2-dimensional model, we see absolutely no change at all because there's no symmetric instability occurring. And in the viscous 3-dimensional model, we see a little bit of flattening and a little bit of lifting, but not quite as much as before. And it seems to happen much more slowly. And that's essentially because of there is still it's very hard to completely eliminate completely suppress the excitement of symmetric instability in the 3-dimensional models. But we have reason to believe that the flattening and lifting of the power spectrum is a result of the excitement of symmetric instability. So I'll just wrap things up here then. So what we've seen is that we might expect to observe symmetric instability in cross-equatorial flows. And that's because of the conservation of a combination of the conservation of potential vorticity and also a change in sign of planetary vorticity at the equator. I've also shown you results from several different idealized models of cross-equatorial western boundary flows. And we've seen in 2-dimensional models and 3-dimensional models the excitement of symmetric instability. And we've also seen the predictions made by linear stability analysis matching up quite nicely with what we see in these numerical simulations. And I've also shown you the effects of the instability on the correlation between the potential vorticity and the relative vorticity, which demonstrates how symmetric instability takes us from a regime in which the relative vorticity dominates the potential vorticity balance to the planetary vorticity dominating that balance. And I've also shown you some how Fourier transforms affect the vertical kinetic energy spectra, so they cause that flattening and lifting. So in terms of where next with this research, so we're currently working on performing numerical simulations on deep western boundary currents, which is really exciting stuff, and we've got really promising results, which hopefully will lead to some interesting, more interesting science. And we've also been looking at applying some of these diagnostics to the LLC 4320 really high resolution MITGCM model run, looking for signs of symmetric instability in there. That's kind of at the borderline of where we might expect. The resolution of that is almost high enough, or is high enough that we might expect to start seeing the signs of symmetric instability. And finally, so this work is it's just been written up, and it's as a paper. It's currently under review at the Journal of Physical Oceanography. But if you'd like to see a preprint and see any of what we read more about what we've done in a bit more detail, feel free to email me at fraser.golds@physics.ox.ac.uk, and I'd be more than happy to share that with you. Thank you for listening.
Yeah, thank you for talking, Fraser. There's time for 5 minutes time for questions. There's one by Stephen already.
Yeah, great talk, Fraser. Do you see any evidence, or have you heard of anybody making cases from observations that you might have enhanced mixing associated with this SI at the equator? It seems like you might be able to measure this if there's this much mixing going on.
So we had to go. I don't know of any So I know of observations of the North Brazil current rings, which have suggested that the potential vorticity in those is 0, or the absolute vorticity. Yeah, absolute vorticity of those is 0. So there's a Bill Johns paper from Castelleo and Johns, I think it is, from around the 2000s, which kind of suggests that perhaps this is going on. So that's quite an old reference. I've not seen any observations of mixing, though, close to the equator. We did try with this work to quantify the amount of mixing which was being caused by the instability, but we basically found very little. But we think that that's a result of the fact that our model resolution just wasn't high enough to model the secondary shear instabilities you get. So you get Kelvin-Helmholtz instability and things which kind of occur alongside this, which we weren't resolving. But those are, it's our understanding that those are really important in terms of producing mixing.
Okay, there's
Great.
another question by Kevin. Kevin?
Hi. Sorry, you said that the vertical structure depended on the viscosity. Can you say something about what Reynolds numbers your simulations were at?
Good question. I couldn't give you the Reynolds number off the top of my head. So we were using a vertical viscosity of around 4 × 10⁻⁴ meters squared per second. I think that's, yeah, per second squared. But then we found that if you stick in the viscosity of water, which is, I guess, about 2 orders of magnitude smaller, what you find is that you get much slightly smaller overturning cells, but with a much bigger, much faster growth rate. So you get a growth, an e-folding timescale of about a day compared to about an e-folding timescale of 2 days, which is what we got here. A vertical scale of around 15 meters as opposed to 100 meters if you use the true viscosity of water.
Okay, thank you.
Okay, there's another question by Steve.
Yeah, sorry, Fraser. The answer to Kevin's question reminded me of a paper in the 1990s by Andy Weaver and others. When you reduce your viscosity and your diffusivity, depending on your numerics, you can expose the solution numerically to an instability that looks, numerical instability that looks very similar to what you're seeing with symmetric instability. You know, numerics and physics often intermingle, and it's hard to distinguish one from the other. So you might pick that old paper up and take a look at it, and just to you know, the numerical instability and physical instability, it's kind of a subtle world when you start reducing dissipation in these models.
Okay, thank you. I'll make sure to have a look at that. You say it was by Andy Weaver, and
I think it was Andy Weaver, maybe Frank Bryan also. It was in the 80s and 90s when people were playing around with vertical mixing and looking at solutions right on the equator. So,
okay.
And we would see it in the overturning circulation. I can't remember. If you can't find it, email me and I'll try to find it.
Okay, thank you.
Okay. Then I also have a question or comment, actually. What you produce by your symmetric instability, you call in the beginning sub-mesoscale, right?
Yes.
It looks more like waves, right? And your W square diagnostics also picking up the waves, the gravity waves, right?
Yes, yes. So yeah, I mean, in the simulations we see as well that we do generate some waves, but I guess what we found quite compelling about that the instability was, or that we are seeing symmetric instability, was I guess the matching between the prediction of the linear stability analysis in terms of prediction of these stacked overturning cells, and we also we definitely do see that very clearly in the 2-dimensional models. And even if we do look at vertical sections of the 3-dimensional models, I don't have any of those to show today, but we again do see these similar sort of stacked overturning structures, and we do see them growing over time, which is.
And another comment which I have, there's a rich literature about zonal currents or zonal jets at the equator. And people also speculated that this mechanism, symmetric instability, generate the zonal jets along the equator. Although Richard Greatbatch can explain zonal jets by other means in a shallow water model, there are experiments which can show zonal jets. Do you also see zonal jets in your models?
So we force these models with purely meridional jets. And we don't have any wind forcing. We literally, sort of, the north and south boundaries just prescribe a meridional jet in and out. I don't think that'd be something which would be able to, or with the current setup, not something we're really set up to investigate with these models, I don't think.
But did you look at the equator? Is there any zonal flow? away from the volume?
Good question. I mean, it doesn't look like it looks like if there is any, it'd be much smaller than. So I mean, we've looked at. So we've not looked explicitly at it, but in these sort of these videos of how the potential vorticity fields vary over time, we don't really see much zonal transport, but compared to the cross-equatorial transport, so the meridional transport. So I wouldn't be able to comment on that really.
Okay. Any other question? I guess Steve is just raising his hand, or forgot to lower his hand, I guess, right? Okay. Then if there's no other questions, also no question from the YouTube stream?
No.
Oh, okay, then we can go on. We are still in time, that's good. Then next talk is by Stefan.
Okay, thank you.
Okay. See the screen, Carsten? Yeah. Okay, yeah, thanks. So I'm going to talk about slightly larger scales. I'm talking about simulating mesoscale eddies in eddy-permitting ocean simulation. So it's basically a parameterization problem that we're facing. On the right-hand side here, so this is, Carsten showed one of these figures yesterday in the beginning of the meeting. This is just the Aviso sea surface height, standard deviation in time. And you can see the western boundary currents, and especially in the Southern Ocean, of course, but especially in eddy permitting simulations, you usually don't get these right. So you have a lot less eddy kinetic energy and a lot less kinetic energy in the ocean. So the task now is, can we improve that? Just to give you an outlook, basically, this is from the model that we're using. This is the finite volume model FESOM2 that we're using at RV, which is an ocean model based on triangular grids. And on the left-hand side, you can see a quarter-degree simulation without backscatter parameterization, this sort of parameterization that we use to enhance eddy activity. And the right-hand side shows you with backscatter. So that's actually an older simulation, so it's not quite as what we are using right now, but it gives you an idea, and this is surface vorticity, sorry. So it gives you an idea of what backscatter basically does. It's re-emphasizing eddy energy in the system. Come back to that in a minute, but basically what we're trying to do is better simulations of eddies, right? And this is from the Aviso data set again. You can see the eddies in the western boundary currents in the Southern Ocean, sea surface height anomalies in time. And as I said, usually most of the eddy kinetic energy is sitting in these western boundary currents in the Southern Ocean, and models at a quarter degree or half degree or 1/6 of a degree, even up to 1/10 of a degree, if you go to the higher latitudes, have troubles simulating these eddies properly. So you're in this eddy permitting regime where you don't really capture the eddies. So what we are faced with is a problem that usually your momentum closure is usually a viscous one. So you usually have a viscous momentum closure, something like Laplacian or Laplacian squared harmonic, biharmonic viscosity in your simulations. But what we are looking for is a better momentum closure that has a more realistic energy dissipation. And when I say more realistic at these resolutions, what we're talking about is less energy dissipation in total. But of course, as we know, so the momentum closure and viscosity is especially also used for stabilizing, for taking care of numerical stability of the models. So just reducing viscosity is usually not working, because then you have then you violate several numerical criteria for stability, and then you cannot run the simulation and it's useless. So what we want is, and I show on the next slide, actually, let's move to that slide, what the important part at eddy permitting simulations is, and you can see here a paper by Soufflé et al. From 2016, where they had a channel simulation, and they ran this at different resolutions from 20 kilometers down to 2 kilometers. And you can see, especially at the 10-20 kilometers resolution, which would be this eddy permitting regime, the slopes are not at all what we expect, like this K-2 slope. This is actually also simulating some sort of sub-mesoscale instability at 2 kilometers, but it's falling off much more rapidly. And the important part here to look at is this dissipation spectrum. And the dissipation spectrum shows you that at coarse resolution, this eddy permitting regime that we are talking about, so quarter degree, for example, the dissipation is not really sitting at the high wave number end of your spectrum, so as in the finer resolution simulations, but it's actually sitting, its peak, it's actually sitting right where the energy is being injected by baroclinic instability. So you're damping the eddies before they can even develop, and you're draining the system of a lot of the energy that is used to actually emphasize the eddies. So there's strong interference with the dissipation and the energy injection scale, basically. And that's a problem. So what the idea is to move this peak here further to the right, so that it's closer to the cutoff scale of the model simulation, so that you're actually only dissipating at the small scales and not at the large scales. And that's the main problem for eddy permitting simulations. So what we want is a momentum closure that dissipates, first of all, the minimum amount of energy, and at the smallest possible scales that are resolved. So basically around the grid scale, but it keeps the model also at the same time numerically stable. And the basic idea, I'm not going into details about this because we have tried several things and with different adjustments. I'm just going to mention some of them in a minute. But basically what you're looking at is the momentum equation, right? So you have here your horizontal velocity tendencies. You have all your classical parts like the Coriolis force, pressure gradient, and so on. And on the right-hand side, you have your viscous operator. So you have a vertical viscosity, but you also have a horizontal viscosity, which we here denote with this V operator. And what backscatter is doing, it adds another operator to the right-hand side, another parametrization operator that is actually the opposite of a viscosity. So it's invigorating the flow. So this is viscosity, and this is the opposite, negative viscosity. And the two together act to still dissipate in total energy, but they dissipate now. This is dissipating at some scale range, and this is injecting energy at larger scales. So on average, you tend to dissipate only at small scales, while you don't dissipate anything at the larger scales. You keep the energy in the large scales. And that's basically the trick. So you're not interfering with total dissipation, so you're still dissipating sufficient amount of energy at the small scales to keep the model stable, but you're energizing in the large scales compared to the viscosity operator. So you always have to view this backscatter parameterization as a combination of a viscous operator and an anti-viscous operator. And the two together go as energy backscatter, what it's called. And this is based on this, well, there are several approaches, but one for the ocean specifically is this approach by Janssen and al. And this comes with another tricky bit, which we also have to address, which is what kind of viscosity coefficient we are using. So you have your viscosity like harmonic or biharmonic, but you also have to have a viscosity coefficient for that. And in triangular grids, this is actually a bit more tricky because we have about twice. So in the specific B type of grid that we have, the velocities are actually saved computed on the centroids of the triangles, while at the nodes, at the nodes, you have all the scalars. So we have about twice as many cells as we have vertices. And that means we have over-defined system in terms of the velocity field. So we need to sufficiently dissipate energy across triangle distances. And we've come up with a new viscosity coefficient that strongly emphasizes the dissipation on this grid nodes so that these two triangles don't become decoupled. And that's another trick that we've used, but I'm just mentioning this. So it's a combination of your viscosity operator, your backscatter operator, the amplitude of your viscosity in terms of the viscosity coefficient, and the amplitude of your backscatter coefficient. And all four of them form your backscatter parameterization in the end. So we've we implemented several versions of this backscatter. So we have a dynamic version, which actually uses a subgrid energy budget. So it basically keeps track of how much energy is leaving, so how much kinetic energy is leaving the system at every time step. And this energy is then available for backscatter, and it effectively scales the amplitude of your backscatter. And this is based on this approach by Janssen et al., also by Klöver et al., some adjustments. The other one is a kinematic backscatter, which is instantaneous. So you have no subgrid energy budget, which makes it cheaper, but it's less well controlled in terms of scale adaptivity. So using different meshes, you have to scale it differently. So in this case here, we just fix how much energy is being backscattered at each time step, and we don't change that depending on the flow regime. So this can become problematic if we move to higher resolutions. We've come up with a new viscosity coefficient that works with these schemes. And then we've done rigorous comparison between old viscosity parameterizations, new ones, and the backscatter parameterization, and tested this both in channels and in global applications. A channel here, for example, is this on the right-hand side. So this is the same that Soufflé et al. Used. So you have a flow from the left to the right. It's a periodic channel on the boundaries east and west, and it's no slip, free slip at the north and south. And then you have some restoring of the density profile to create a current. And this is just a summary of basically these channel simulations. You can see here at 20 kilometers, so that's about a quarter degree. You can see two classical viscosities that we've used in FESOM. So there's a sort of upwind type of viscosity and a leaf viscosity here. And then we have a 10 kilometer control that is much higher resolution. So it's half the resolution at 10 kilometers. This is the eddy kinetic energy profile in the vertical, top layer on the top, bottom layer on the bottom, 4,000 meters depth about. And you can see that at 20 kilometers, the classical schemes have a lot less kinetic eddy kinetic energy compared to the higher resolution simulations. And if we use this dynamic or kinematic backscatter, we even outperform the 10 kilometer resolution. So this is not saturated in kinetic energy at 10 kilometers. There's still something to gain by going to higher resolution, but basically both kinetic and dynamic backscatter, kinematic and dynamic backscatter improve the simulation substantially by a factor of close to 2, right? Or it's 70% or something like that. So that's good. Also in this channel simulations, we can look at dissipation rates, and you can see here, this is different layers, but basically look at the bottom layer here. So this is 4,000 meters depth. The dissipation rate for upwind and the leaf scheme, the classical viscosity schemes, are about an order of magnitude larger total dissipation compared to the backscatter simulation. So we reduce kinetic energy, we reduce the dissipation and increase the eddy field with that. But then we move to actual global simulations, and this is this plot. Again, this is Aviso, sea surface height, standard deviation, what we want to achieve. And on the right-hand side, this is, on the left-hand side, this is a reference simulation without backscatter, relative difference between the observations and the reference. So if it's red, it means there's more variability in the observations compared to the reference, and this by a factor of up to 3. And on the right-hand side, you can see that if you compare the observations to the simulation with backscatter, in this case, this dynamic backscatter, we reduce these biases substantially, especially here in the western boundary currents in the Southern Ocean. You actually remove this nearly entirely. Of course, there's some overshoots, and it's not perfect, but it's much, much, much better. Similarly, if you look at currents, so this is just a snapshot of currents here for backscatter and without backscatter. You can see the flow becomes a lot more variable. You can see more eddies forming here of the Agulhas current, for example. Also, the Malvinas current gets this horseshoe shape a lot better, and the Kuroshio's similar results. And if we look at the sort of actual mean currents, here this is mean sea surface height for different currents. In the top for backscatter, in the bottom without backscatter, in the middle just the Aviso simulations, the Aviso data from the observations. And I would just want to highlight, for example, the Malvinas current. You can see this tongue of the cold tongue that goes upwards to the north is well captured with backscatter, but it's not at all captured without backscatter. And similarly, also the gradient here across the Gulf Stream, it becomes much better. It's much steeper in the top than in the bottom. Of course, we don't quite get the corner here, the northwest corner right. It's still too far. It's still too zonal, but it starts to appear compared to here, to the without backscatter. So we're not just re-emphasizing the eddy field, we're also improving the mean currents. That's the main message here, that the effect of the eddies also interacts with the mean flow, and then we also improve the mean flow. And finally, also to look at temperature biases. So obviously you don't want to improve just the velocity field, but you also want to look at what happens to temperatures and salinities. This is just a transect through the Indian Ocean. The bias to climatology with respect to reference, and here with respect to backscatter, and the difference between backscatter and reference. And just by eye comparing these two plots, you can see that this warm bias in the reference basically disappears in the backscatter case. So we are not just improving the mean currents, we're not just improving the variability of the currents, we're also improving the temperature distributions. And similarly, you can see this here. This is now with kinematic backscatter. So both dynamic and kinematic have similar results. Dynamic is a little bit more accurate, while kinematic is cheaper in the implementation. But again, you can see here in the right, this is backscatter, and the left is the reference. And I just want to highlight two regions here. The Gulf Stream cold bias that you usually have because of the wrong path of the Gulf Stream is reduced with backscatter. And similarly, the warm bias in the Southern Ocean here is also reduced with backscatter, and that at different depths. So this is 500 meters, and here it's 1,000 meters. And you can see also here, this outflow of the Mediterranean is improved with backscatter, and the Southern Ocean is decreased the bias. And just to summarize this, so we just looked at mean values here, mean diagnostic values. So for mean sea surface height, the bias is improved by something like 11% globally, and up to 21% in the Agulhas current. So depending on where you're looking, you get, of course, better results. But on average, over the entire globe, we have an improvement in the mean sea surface height bias by 11%. Standard deviation is similar, it's about 7%, but it's very, very strong in the Agulhas current, for example, or in the Southern Ocean, where a lot of eddies are. So the variability is much improved there, up to 40%. And we have these improvements also for temperature biases. So globally in the surface, for example, it's again around 10% in salinity and temperature. But for this Indian transect, for example, which I highlighted, of course, because it's the best one, we have 30% or about 30% for salinity and temperature. Yeah, and I think that's it. So we've implemented new viscosity coefficients and different backscatter schemes that lead to substantial reduction of total dissipation by about an order of magnitude. We have substantial improvements in eddy variability and mean currents and temperature and salinity, something between 10 and 40%, depending if you look globally or regionally. One drawback we saw is that we have a deterioration of the Antarctic sea ice because we have increased subsurface temperature bias in the Antarctic, which I didn't show. But this is basically just a scaling thing, and we already basically fixed this. This is the next publication that we're coming up with, where we just scaled it in the Southern Ocean because we're too vigorously backscattering in the Southern Ocean close to the shelf of the Antarctic continent. Yeah, and then just one final note here, dynamic backscatter is scale adaptive, so it runs with different resolutions, and you can even use it on an unstructured mesh, which is good, while this kinematic backscatter is, you have to always tune it for each resolution, but on the other hand, kinematic backscatter comes for free, it doesn't cost anything, while dynamic backscatter has an additional cost because of the subgrid equation that you need and another prognostic equation, and you have to do a lot of smoothing for this field. And that's all I wanted to say. So maybe I'll leave this as the last slide.
Okay, thanks a lot, Stefan. There's a question by Laura.
Yeah, thanks, Stefan. That was great. Very interesting talk and very nice results. So one question you answer in your last slide, which is you should have the positive, but I was wondering what the negatives were. So you told us on that part. One technical question is, so basically, the viscosity as a vertical profile, what do? You do it per layer, so you backscatter for each layer independently? And then again, do you get vertical biases because of that?
So we do
something you've looked into?
Yes, so I've actually tried doing it barotropic, so using just one equation for the subgrid equation for the entire water column, and that didn't perform very well. So I moved to baroclinic, having at each layer a different subgrid equation, and that was a substantial improvement actually. I didn't see any trouble because of that, but again, we haven't looked into all the details yet. So there's still some things like enhanced diapycnal mixing that we might have to look at. If this is a problem in some regions, we know that for kinematic backscatter, so where you don't have the subgrid equation, where you just energize with the same coefficient all the time, that you can run into this regime where you create too much vertical waves and you actually destabilize the water column. So that there are issues with that. Too much mixing can come in, but especially you can create vertical waves that are propagating from the surface down to the bottom that create unphysical results in terms of numerical noise that you have to be careful with. So especially for this kinematic one, we have to look at these things specifically for each resolution, but you can tune it away basically. So you have to be a bit careful. You have to know which knobs to turn, but it works in that sense. But yeah, yeah, you have to be cautious with this. Yeah.
Great, thanks.
Okay, any other questions or comments? Are there questions in the YouTube stream? No?
No.
Okay. I have a comment actually, Stefan. This method is kind of cheating, right? Because in principle, the eddies which you simulate should do the upscale energy transfer, but you just put this energy in the large scales. So I wonder how far can you do this? Can you just implement another parameterization which makes the Gulf Stream right, just by pushing the Gulf Stream northward? And how far can you do this?
I mean, of course, I mean, if you really want to go to relaxation or something, you can do whatever you want, right? You can make the model look as good as you like if you do, but this is not a relaxation, right? We're still relying on the dynamics to propagate the energy to the right places. So we're not prescribing anything where it should be. We're just allowing the system to evolve more. But you're right, it's a numerical way of reducing dissipation. So it's not to be confused with actual physical backscatter from the unresolved scales. What we are doing is we're just reducing the amount of energy dissipation by adjusting the viscosity parameterization is also ad hoc in a sense, right? So if you use Laplacian from the Navier-Stokes equations, it's come from molecular viscosity, but what we're simulating is not molecular viscosity. So there's no profound reason to use a Laplacian for your viscosity closure. So basically what we are using is a more complicated operator for the closure. And what it effectively just does is that it allows for less energy dissipation, but still sufficient amount of entropy dissipation to keep the model stable. But again, I think that the good thing is that this it scales with resolution, at least this dynamic backscatter. If you go to regimes where you actually fully resolve the upscale propagation of energy, then you don't the backscatter will scale down automatically. So it scales with resolution in that sense.
Okay, there's another question by Steve.
Stefan, yeah, very nice work. One of the things that we had problems with is boundaries. You know, the inverse cascade is something that, you know, is free space. There's no boundaries. When you get near boundaries, did you see any funny things happen? One of the things that we would see is some boundary currents, like near some islands, go in the wrong direction. That was early implementation, and I'm probably revealing things that may have been fixed by now, but did you make any special considerations of how you treat this backscatter when you get near boundaries?
Actually, we are working on one version or one adjustment we did, which will incorporate this in a sense. But the version that I showed now actually doesn't do that. So that was the surprising thing. I also expected this when I ran the channel, and then I moved to the global simulations. I expected that I would have to damp it near the boundaries. I would have to damp it near the bottom topography. But none of this was necessary, and we didn't see these artifacts really, which might be, I think, if I speculate, the reason for this will probably be because we are injecting the energy on relatively large scales. We're using several smoothing operations, so it's not just bi-Laplacian and Laplacian for viscosity and backscatter. It's actually a very smooth Laplacian. So the scales on which we backscatter are relatively large. And I assume that even in the boundaries, you still you don't excite these type of very narrow features that you might see if you don't use a sufficiently strong smoothing operation there. That's my speculation on this, but we didn't see this. I mean, the only thing we saw is the Kuroshio at some regions was too strong in terms of the energy injection, but that is also a combination with the forcing as we see.
Thank you.
Okay. There are no other questions. Then we should go on to the next talk. And that's a talk by Boris Galperin on a analytical theory of oceanic and atmospheric spectra. So Boris, please share your screen and start your presentation. And we are a little bit over time now, but maybe we can shift the whole program a little bit by 5 minutes. I think that we can do, right?
It doesn't want to share for some reason.
We can see your screen.
Right.
Oh, you can.
Yeah, but your full screen, your desktop.
No, this is okay. This is easy to fix. Okay. So let us. Sorry. Is it better?
Okay. Can you make it full screen?
Okay, I'll do it in a different way. Can you see it now?
Great.
All right, I just need to, okay. So it's more analytical work than other presentations. Well, first of all, good morning. And I'll continue. So it's more analytical than other presentations. And this work had contribution from Simeon Superiansky in Israel and Bochu in Hawaii. So to start it, I would mention three criteria of kind of inconsistencies of the model mentioned by Karsten yesterday. And I'm going after the third one. It's inconsistent numerical and mathematical theory. So what my presentation is about is mathematical theory. And the main idea is to develop analytical theory of anisotropic turbulence with waves. And the anisotropy is caused by extra strains, which are strains additional to the basic shear. And the strains are caused by stable stratification, rotation, beta effect, it can be magnetic field as well, and other factors. So we'll start with the basics and recall that in traditional three-dimensional turbulence, isotropic turbulence, homogeneous isotropic turbulence, the energy spectrum is given by the famous Kolmogorov equation, Kolmogorov constant Ck, pi epsilon, it's energy flux. Usually they use a viscous dissipation rate, but using pi epsilon is a more general approach, and it was suggested by Robert Krachman some many years ago. And the wave number to the power of -5/3, it's a famous -5/3 law. And the underlying idea here is also very old due to Richardson, and large worlds go to small worlds and transfer energy to smaller and smaller scale. So it's energy, Richardson's energy cascade. Now, this is a simple equation. And if we know that spectrum is determined by only two parameters, energy transfer rate and wave number, then the power spectrum comes out, and also the power law of the energy flux come out from dimensional analysis. But of course, the question, how do we know the Kolmogorov constant? It's a big deal. And if we use dimensional analysis, then we can only use experiments or some analytical theories, which are only available since, say, 60 years ago. So we need to remember that when Kolmogorov developed this theory, his insight was that he needed to use the rate of energy flux. This is not a variable which enters the Navier-Stokes equation. He needed to step over to the energy equation, and from energy equation it follows very well. But it also gave us an idea that energy, the spectral amplitudes always depend on fluxes of energy or entropy, or if it's scalar fluxes, scalar spectra, they depend on scalar fluxes and so on. So this is a kind of a leading idea which has been driving development of turbulence theories and turbulence models since their inception, that the spectral amplitude is determined by the spectral flux. Now, in geophysical flows, we have these extra strains. They were first kind of systematically described by Peter Bradshaw also a long time ago. But the moment you add these extra strains, you add a lot of new variables and a lot of new dimensions. So what do we do with dimensional analysis? How do we determine the spectra? This is not clear at all. And we do some experiments and observations, but they don't always help because we just had too many parameters. So it would be better if it could be guided by some analytical theory which can systematize, present everything in a systematic way. So this was one of the main subject of our research, and we developed analytical theory of turbulence, which was later developed into anisotropic turbulence. And the theory name is quasi-normal scale elimination, or QNSC. In one slide, this is a theory which deals with turbulent flow, which is commingling of fluctuation on all scales down to Kolmogorov scale, and strongly coupled fluctuations. Turbulence is not amenable to standard perturbative methods because the expansion parameter Reynolds number is very large, so it's just diverges very quickly. Now, the QNSC is a successive coarse graining model of the initial domain, and it produces renormalized molecular parameters in terms of the eliminated scales. In other words, the main purpose of this model is to produce subgrid scale parameterization, be it viscosity, diffusivity, or anything else which you want to renormalize. Okay, so in addition to subgrid scale parameters or coarse-grained subgrid scale parameters, it also produces expressions for universal constants, such as Kolmogorov constant and many other constants. And of course, this theory goes far beyond dimensional analysis. So here I will only, so far we have developments for stable stratification and rotation separately. And of course, big task is to put them together. So today I will only be talking about rotating flows, and this is turbulence with inertial waves. And it's only the tip of the iceberg of what we have done. So we developed the spectra. It's a longitudinal spectrum, it's in yellow, and transverse spectra is in green. You can see that it has Kolmogorov part and K2-3 part, but this is not entropy flux. This is Coriolis parameter squared. And it has different coefficient for longitudinal and transverse spectra. Transverse spectra is about 3 times bigger, but not exactly 3, it's 2.6. It makes a big difference because for 3 it would be two-dimensional turbulence, but this is not two-dimensional turbulence. Now, when we developed the theory, it was purely analytical theory, abstract theory with no applications. And the first thing which I wanted to see is how it applies to flows which we know. So we applied it to the spectra by Nastran and Gage, atmospheric spectra. And to our surprise, the theoretical results went right over the data. You can see it on this picture. Of course, we needed to know what is energy flux here, but it was determined by other people. We didn't want to do any data fudging. So we just took the number from the paper by Freilich and Sharman. And this is what we got. You see that the agreement is very good for zonal spectrum and meridional wind. This is both longitudinal spectra, it's not transverse spectra. And there's no geostrophy applied, anything. It's just a straightforward application of the theory. Now, the Nastran and Gage don't provide any data with this. It's only longitudinal spectra. We also wanted to see what transverse spectra would be doing. So we took another data set. It's from Mosaic, and the data developed by Callias and his group. And here you see the blue and red line for transverse and longitudinal spectra for Mosaic data set. It's similar to Nastran and Gage, but different locations, different time, and different providers of the airplane. And the agreement here is also very good on practically all scales. There are some other things I just don't have time to go through this. Now, we also paid attention that there's longitudinal dependence of the spectra, which wasn't discovered, wasn't studied by Nastran and Gage. They just did the averaging over the longitude, but you really cannot do it because the spectra do depend on the longitude. So it's one of the conclusions which we saw right away. Now, what does it have to do with oceanic spectra? Charney in 71 said it is thought that the above theory, which he developed and which is geostrophic turbulence, should also apply to the oceans in the region of strong baroclinic excitation, such as the region of the Gulf Stream meanders. But no data was available then. Now, if you look on the expressions, we only have dependence on pi on the horizontal energy flux and Coriolis parameter. So there is I mean, there's no reason not to expect universality. And we wanted to see how this spectra would compare with oceanic spectra. So we used ship-mounted ADCP data in many locations. We did it on purpose because we wanted to avoid any mentioning or any use of geostrophic approximation. This is just straightforward data. And I have this it's incomplete list now of all the data which we used. We now have the data all the way from Arctic to Antarctic across the equator. And in all cases, we have pretty good agreement with the data. So I just give several examples. This is Oleander mission. You can see this is the trajectory of the ship between New York Harbor and Bermuda. It was commercial ship still going on. And this is velocity ellipses. So you see what when I go through the stream, there is strong anisotropy, and it can affect the spectral calculation. So there was a paper by Bowler in which they introduced some mathematical procedure to get rid of this anisotropy to make it kind of more regular. So we compared with his data, and you can see this is our lines are dashed, and his are blue and red, again, transverse and longitudinal spectra. But what happened, without his correction, we couldn't get the amplitude right. Our amplitude, it's about 40 degrees. We only could do it with 60 degrees because this anisotropy put too much energy on large scales. But when we used his correction, we could do the right amplitude, but it bumped the small scale energy by order of magnitude. So this first analysis was done by Dingping Wong, and he gave me the data later, which was going only to just under the Gulf Stream. And when we compared with his data, the agreement was very good, right? With the theory, we didn't have anything to improve the agreement. The next one, we thought, okay, if we know that there are two branches to the spectrum, so maybe we can use small scale branch, Coriolis part, not Coriolis, Kolmogorov part, to characterize subgrid scale seasonal variability. It also, there's more than I show here, but I think this is the most interesting result for Northwest Pacific Ocean done along this cross section, which covers 4 different areas: Kuroshio, subtropical contrcurrents, North Equatorial Current, and North Equatorial Contrcurrent. You can see all of them. We know the latitudes for each one of them, so we can study, we can plot the spectra in each one and compare with the estimations from the data, which was published by Bo in 2017. But we did it with initial data, which was annual average, but then he has a later paper in which he did evaluation of spectra as a function of the season. So you can see that we have pretty good agreement with all 4 regions for all seasons. The red is a springtime, and which is more energetic a little bit, and blue is summertime, which is less energetic. Of course, it's not always agrees. In Kuroshio, I think we have the same problem as in the Gulf Stream, and anisotropy causes the spectra to go a little higher than it should be. But in other allocations, the agreement is pretty good. Nobody was in this conference so far mentioned intermittency of turbulence. Intermittency may be caused by the waves, and this is why we don't have consistently transfers larger than longitudinal spectra, which would be expected from solenoidal fluids. It goes up and down. It may change as a function of the distance, and it may be caused by this intermittency, which we haven't studied. So the variable which we plotted here is 1/2 of longitudinal, one-dimensional longitudinal and transverse spectra. Sometimes it's called kinetic energy, but it's not kinetic energy, it's just sum of the 2 spectra. But since this is what was measured, we could compute it from this theory and plot it against the data. Now, what we see here, I will show it later in the paper, that the horizontal flux really becomes bigger in wintertime and smaller in summertime, because turbulence also changes in intensity. So the idea was maybe we can measure the mesoscale, maybe we can measure seasonal variability in terms of this one parameter pi epsilon. And if, now also I need to mention here that every region here is in a different latitude, and using the correct latitude was absolutely crucial. Without using the correct latitude, we couldn't get agreement at all. And another thing that when you go close to equator, like this area, the effect of Coriolis parameter becomes very small, and the spectra, as you can see, can be described by Kolmogorov branch to very high wavelength, to have very high scales, almost about 200 kilometers. We cannot do it with any other location but close to the equator. We also introduced a scale LC to transitional scale between Kolmogorov and Coriolis branches, and it can be used. Now we can associate the Kolmogorov branch with submesoscales and Coriolis branch with mesoscales, and the transition between them is a scale LC, which is a function of L omega. L omega is an analog of Osmedov scale, but instead of Brand-Vasali frequency, we use Coriolis parameter.
2 minutes left.
All right.
2 minutes left.
So LC changes the same way as pi epsilon. What we saw that was that this pi epsilon, this energy flux changes between, it's a little bigger in summer, in winter, a little smaller in summer, and it fluctuates around the annual mean, which is in between. So indeed, we can do quantification variability in terms of one parameter. The mesoscale variability, on the other hand, is very limited because it's related to F, and F is a constant variable. Now, what determines the spectral amplitude? That's an interesting question. So we can go and say that it's determined by spectral entropy flux. And if we do this, then we show we can use the data from Lindbergh in '99, and we find that it agrees with our latitude of 34 degrees, more or less. But we cannot determine which theory really works. We need another set of data. So there was a paper by Hattie in 2018 in which he did independent estimate of fluxes using, well, this geostrophic current and also model. And when we compared with, well, he estimated the flux to be 10 to minus 18 of second to minus 3, while Lindbergh flux was 10 to minus 13. There is a 5 orders of magnitude difference, while the spectra are more or less the same. So this gives you another indication that the spectra are not really determined by the entropy flux, but by the Coriolis parameter. And now I can go to the conclusions. The QNSC theory extends Kolmogorov theory to turbulent flows with anisotropic extra strains. And the spectral amplitude on large scale are determined by extra strain rather than fluxes. While we can recover some well-known spectra and we give them different interpretation. We see that the spectra are latitudinally dependent. And the theory, which is very important, it predicts both spectral slopes and amplitudes. We cannot go with slopes only. And if you look on the literature, most of it deals with spectral slopes and says nothing about the amplitudes. And this is not surprising because we don't know what to do with amplitudes. We cannot determine them from anything else but analytical theories, and they just didn't exist before. Now, we introduce this on submesoscales of pi epsilon, we call it equivalent submesoscale dissipation. And with this parameter, we can quantify seasonal variability on submesoscales. On mesoscales, you can see on many data that the variability is limited by the dependence on the Coriolis parameter. Now, very important thing, which I probably say this for the first time, rotation causes turbulence to exhibit properties of a flow with compactify dimensionality in such a way that it exhibits properties of a flow with dimension bigger than 2 but smaller than 3. Another thing is that on large scales, in flow like this, we can develop dual cascade. You can have direct cascade and inverse cascade on the same scales at the same time. And this feature releases our flows from the curves of inverse cascade, because otherwise we don't know how to get energy from large scales to small scales, because then inverse cascade will bring it back to large scales. And we haven't tried it yet, but the main product of QNSE is pi-dependent expressions for flow-dependent subfilter scale or subgrid scale parameterizations, which yet to be tried in numerical oceanic models. They are being tried in atmospheric model in WRF, and they have pretty good success there, but we still need to try them in oceanic models. And this is the end of it. Thank you, and I will be happy to answer the questions. And here are my conclusions again.
Okay, thank you, Boris, for this talk. There's a question by Jack, but before we answer this, all people who are not interested in the answers to Jack's question, they can go already to the break. We will meet again at 3:25, and until then we can discuss. Okay, Jack, go ahead.
Yeah, so in the spectral prediction that you showed at the beginning, at very large scale, so you have a K to the -3, just like in observations, just like in QG turbulence, but it's a theory which doesn't have any stratification. So I just don't know how do you, I mean, if we believe, I mean, you cannot believe both in your theory and in the fact that the large scale is controlled by something like QG turbulence.
Well, our supposition now is that the rotation affects scales in the horizontal, has the biggest effect in the horizontal, and stratification has the biggest effect in the vertical.
But I mean, in QG, stratification is completely key to the whole thing, right?
This is true, but QG also gives you the spectrum dependent on the entropy flux, and this is not what we see. So I'm not saying that we need to revise QG, but we may be heading in this direction. We need to develop a theory which will have rotation and stratification together, talking to each other and interacting. And when we have it, then I will be able to answer your question better. There are a lot of things going on in nonlinear dynamics, which we just don't appreciate and don't know yet. So I will not speculate on this.
Okay, thanks.
Okay, I think the second question was by Steve.
It's kind of a follow-up to Jacques' question. I mean, you have the first bullet on this in this conclusion, QNSE extends Kolmogorov. I'm puzzled by how you're thinking about this. I mean, you got SQG, which can give you K to the -5/3. You've got, various submesoscale instabilities in the upper ocean that can give you K to the -2. You have QG that can give you K to the -3, and they are not, homogeneous isotropic turbulence like the Kolmogorov theory. I'm just wondering, do you mean that you're extending, this sort of philosophy of Kolmogorov, with statistics and spectra, or do you really think that, with anisotropic extra strains, you can, Kolmogorov is God and everything is Kolmogorov? I'm just trying to see what you're saying with that first bullet. Is Boris still here? I don't see him.
Yes. I'm still here, and thank you for your question. Well, I will answer you with a question to your question. Our theory predicts slopes and amplitudes. You mentioned other theories, but can this theories predict the amplitudes? SQG and other, I never saw that they could predict the amplitude. So let us see if they can do the amplitude, and then we shall do the comparison.
That's a good question. I mean, I always sort of implicitly thought the amplitude was determined by the forcing.
Apparently,
right?
It's not. It's kind of a thing, not new thing, which I didn't say anything about. We have an experiment in big rotating tank in Torino, And we wanted to study zonal jets, but the regime was far away from zonal jets. And we got some spectra and started looking at them, and they look just like the spectra which I just showed. So it seems to be really quite a universal spectrum, which we only begin to appreciate now. Okay. The question which you asked and Jack asked, I cannot answer until we have the theory of rotation and stratification working together.
All right, thank you. Very provocative.
Okay, there's another question by Yaron.
Thanks, Carsten. Thanks, Boris, for the talk. I would just like to ask whether you can give us some intuition, because it's kind of similar to magnetohydrodynamics, where when fluid mechanics, when you are like putting some external forcing and the turbulence switches to more toward the two-dimensional. And your claim here is that when you have the rotation, it affects kind of in a similar way where it pushes it to the two-dimensional. So could you give some physical intuition? Why do we expect this to happen when we have the spinning of the globe?
There was a bunch of papers several years ago, I think in physics of fluids, and they were discussing this transition of dimensional transition of turbulence under the effect of extra strains. I think it was Bob Ecke and the guy from Torino. It's a famous guy, but I just need to remember his name. Well, anyway, they consider the triad interactions, and they can be split in 4 different groups. Mm-hmm. And helicity plays an important role in one of these groups. What happens with this extra strain? They change the relative contribution from these 4 groups. And this change is equivalent in a way to the way they would behave if you change the dimension of space. And from here they went to this representation of the effect of extra strains as moving the flows into the category of flow in dimensional bigger than 2 but smaller than 3. And they called it compactified dimensionality. These flows do develop dual cascade. It's very important. You have dual cascade, direct and inverse cascade at the same time. And in our theory, because the spectrum is determined by the Coriolis parameter, it really doesn't care about the relative importance of this cascade. You can change them with a weight number or with a scale, but the spectrum will not feel it because it goes like f squared k to minus 3, f is constant. All right, so this is how it all comes together. Mm-hmm.
Yes.
But even these people, they just published a big paper on extra strains. It's one of them is Alexakis. It's about 100 pages paper in which they discuss different modification of flow by extra strains. But even they didn't compute the spectral amplitudes because even they don't have analytical theory. So in this respect, our theory is quite unique. Mm-hmm. And it's what can I say? It's you cannot deny that there is sensitivity to the latitude. You cannot deny that the spectrum in the equatorial region becomes more or less like Kolmogorov spectrum. And there are many traits in the spectrum which we actually observe in the real flows in different environments, both in the atmosphere and in the ocean.
Okay. I think we should stop the discussion here and have a half-minute break, and then we can start the next session, okay?
Thank you.
Thank you.
Okay, Manita, it's your turn.
Yeah, I will start in a minute. Okay, welcome everyone after the break. And we now start the second session for today, beginning with Carsten Eden, who is also the speaker for TRR 181. And he will talk about a closure for Lee wave drag on the large-scale ocean circulation.
Okay, so this talk is about a closure for Lee wave drag, as Manita said. And that's work in collaboration with Thomas Eriksen, a PhD student here in university, and Dirk Olbers from Bremen. And here, this is a sketch about Lee waves. If there's a flow over some topographic obstacle, we can have Lee waves generated, and they have a frequency of encounter which is 0, but the intrinsic frequency, which is this one here, it needs to be between Coriolis frequency and the stratification frequency. And if this condition is met, and if the K here, which comes from the topographic spectrum, and the flow speed matches this relation, then we have these Lee waves. And different to normal gravity waves or linear gravity waves, we do know here the amplitude and so the energy of the Lee waves which are generated from the kinematic bottom boundary condition, which applies at the bottom where z equals minus h. You have condition on W, and if you go to Fourier space, you have from the topographic spectrum here, this h hat and the flow, you have the spectrum of vertical velocity, and from polarization relations, you get everything. You can calculate everything which you need to know about the Lee waves. For instance, the vertical flux of energy, which is P times W, and this is of course long known since Bell maybe. And from that you can integrate over the wave numbers and get the total energy flux. And this has been done, of course, several times. And what you get, or what you need for this to calculate this globally, is you need the observed bottom flow at the ocean bottom and the topographic spectrum, where there are ways to get the topographic spectrum. I will come back to this later. And what you get as energy transfer from the mean flow U to the waves, to the Lee waves, is this number, 0.1 to 0.75 terawatts. And this is comparable to all the other energy transfers, maybe from the atmosphere to the ocean by the winds or by the tides. This is a similar number. So it's it's an important process in the energy cycle. And second, it's also important for the dynamics, not only for the energetics, but since the stress on the mean flow U by this generation of the Lee waves at the bottom and also in the interior when the Lee waves propagate upward, that was shown by Alberto, for instance, that can be actually quite large. We can compare to the surface wind stress, and at places, and we will see this later also, it can be as large as the surface wind stress. And you wouldn't neglect the surface wind stress for forcing an ocean model, so you should also not neglect the bottom stress by the Lee waves. But the problem is that you don't know how this tau, this wave stress, distributes over the vertical. And therefore, it's difficult to implement this in ocean models, and therefore, it's usually not accounted for. And this, of course, we want to resolve here. Starting point is are these relations for gravity waves in general, which also apply to Lee waves. There's the dispersion relation, which might change over space, and group velocities in horizontal and vertical group velocities, and also refraction parameters. If we have X and Z dependencies, then horizontal wave number K and vertical wave number M change. And the wave energy, which we are interested in, is governed by the radiative transfer equation. And this equation is then the basis for the closure. And it has different names, Boltzmann energy transport equation or kinetic equation. Actually, yesterday, Jacques called a very similar equation for the amplitude of the waves, kinetic equation. It's very similar here. On the left-hand side, you have transport terms, transport in physical space and transport in phase space, because this wave energy is a function of physical space, X and Z, and also of phase space, K and M. On the right-hand side, you have interaction with the mean flow. It was also actually in Jacques' equation yesterday as a scattering integral. Here it's It's this simple relation. And another term. If we look at the first two terms, they are actually the propagation of the wave energy or of the waves in physical space. And we can make that simpler if we assume here lateral homogeneity. That means all the x dependencies we ignore. Then the first term just drops and we only have the second term in the wave equation. And then also if you look at the horizontal change in the change in the horizontal wave number, see it also drops. And then we also have no effect of this third term here, of the third propagation term in the radiative transfer equation, makes it simpler. And therefore we assume this, but can also relax this assumption, but it makes it here, this discussion, much easier. On the right-hand side, we have first term here, that's the interaction with the mean flow, or it can be interpreted as an energy transfer actually from to the mean flow. If there's z dependency in the u is the mean flow. That was this one here, flowing over the topography. And if there's z dependency, you have an energy transfer. It's related to wave drag, what you usually, or what meteorologists actually call wave drag in the atmosphere. If there's also an x dependency in the u, you would have more terms here on the right-hand side with lateral gradients in u, and that's usually or sometimes called wave capture or related to wave capture. Then finally, the S term here, that's maybe the tricky part. That contains any forcing function of the waves, flux at the bottom for Lie waves, but also dissipation, which is maybe wave breaking, nonlinear process already. And also all other nonlinear processes, in particular wave-wave interaction. So an energy transfer between waves at one K to waves at another K. That's wave-wave interaction, which is here subsumized under this S. And the idea for this closure is similar to our ID-mix closure, of course, is that we want to integrate this radiative transfer equation in an ocean model, and similar to the other equations which we have. And then we can predict the wave energy and we can predict all the consequences, what the waves do for the mean flow. But of course, the 6 dimensions here, there are too many and we have to reduce them. And we do this by integrating in wave number space. So integrating over M and over K, this equation. Then we get this equation here for the energy compartment E here. And what we did is all terms have been integrated over vertical wave number M and also over wave number amplitude K. We have split it here, or we have represented K here polar wise into an amplitude and a wave number angle phi. So this E here still depends on wave number angle. We only integrated over K and M and still on Z, of course, on vertical coordinate. And what's also done is here, it's not integrated over all the wave numbers, but only those which have either positive or negative sign of the vertical wave number Z dot. It's a vertical propagation group velocity Z dot. And that the reason is that we can, by doing so, we can differentiate between upward and downward propagating waves. And that makes it easier to parameterize here the S term at the end, because that needs parameterization in this closure. The parameterization in a closure is needed here to parameterize this term. And it's easier if we differentiate between positive and negative sigma, which is the sign of the upward or downward propagating waves. And for Lie waves, it's a bit complicated. It's not just the sign of M, which it determines here the sign of Z dot. It's also the wave angle, which in relation to the mean flow, which is important. Then all the other terms are also integrated. From the vertical propagation term, we have this bulk vertical group velocity and this bulk exchange parameter lambda, which are similarly integrated. And to get expression for these two here, we assume as an ID-mix a fixed spectral slope, but with variable amplitude. So here you have our expression, our model expression for this Lie wave energy. There's some spectral shape function A of K and phi, and then the M dependency is expressed by the delta functions because they have the Lie waves have fixed vertical wave number for given frequency and wave number. And if you integrate over this stuff here, the A is normalized. You pick by integration over M either the E plus or the E minus, which is exactly this compartment here. And but this is of course a variable. This is a model variable here, the E plus and E minus. And the task is then to specify the spectral shape. And we do so by assuming Bell's linear theory, which we had here from this P times W. We can calculate the flux of the energy, and flux of energy is also Z dot times energy. So you divide by Z dot and you have the energy shape of the Lee waves. But there's one complication because there's a singularity. So what we need to put in is damping in our Lee wave approach, the linear Lee wave theory by Bell, that introduces this friction parameter R. And the reason is a resonance catastrophe near F or at F actually. There's, you divide by 0 and then the Bell's model blows up in terms of energy. So we damp this away with a small friction parameter, which is much smaller than F. And then second ingredient is you also need a topography spectrum, and for that we need the statistical description by Goff. And then it follows very simple relations for this parameter lambda and this Bulk group velocity c. And this lambda 0 is involved everywhere, and it can be approximate. There are exact expressions which involve integrals, which are nasty, but they can be approximated very well by this expression here, where you find the R. That's then the free parameter which we have to choose to determine these parameters in the simple model, which is this one here. And then finally, and then there's also the stress, of course, which we need to put in the model, which we can calculate using this relation here, either in this representation or in the wave amplitude representation. And what we use is the pseudo momentum flux. You have a momentum flux, actually an actual momentum flux, the first one here, and an effect in the buoyancy equation, but you can combine both to a pseudo momentum flux. Then you only need to put it in the momentum equation, and the momentum equation you model is then the whatever the residual momentum, or how you would call this, doesn't matter. And that's the stress, and the stress divergence you put into the mean flow equation. That's how simple it is. And the remaining task is then to integrate the stress over K and M, this is here, but then also to integrate over the wave number angle. Then you have compartments which are only functions of Z anymore. And X if you put this in the model, of course. And these are the model equations, quite simple. There's vertical propagation for the upward and the downward propagating wave compartment, and exchange with the mean flow here.
Carsten, you have 2 minutes left.
Oh, already. Okay, and for the S term, we need parameterizations, symmetrization in M. This is one part of the parameterization for S. The other one is to take energy out, and for that we need what we know already from IDMX, a quadratic form in energies. One of the energies is GM energy and the other is Lee wave energy. So this term takes out energy. This makes the symmetrization. It damps away the difference between E plus and E minus. And okay, there's one part now which I want to show is the validation. I want to skip this here. That's a direct numerical simulation of this radiative transfer equation for energy without any approximation, except for the S term, which we use the damping. And then you can actually tune your parameter R to fit the Lee wave closure to this direct numerical simulation of the radiative transfer equation. So I skip this here. And then I can come to the integration of the Lee wave closure itself and some idealized examples. Here, this is a simulation of this energy compartment without any symmetrization or dissipation, only forcing of a flow at the bottom. You see here, then energy goes up. It's reflected at the surface, goes down as E minus. The U is reduced by the divergence of the momentum flux. And then at the end here, you have no U anymore, but all the energy is stored in the Lee waves then, and then the model doesn't do anything anymore. So that's not very realistic. So can put in symmetrization and dissipation. And this is shown here. And an idealized example again here, U profile, N profile. What you get in the steady state are bottom intensified energy levels, and this is how the stress looks like. And you can also calculate the vertical turbulent diffusivity from Osborne-Cox relation. It's bottom intensified as you might have expected. What we also did is we put this then from the idealized case directly into a realistic global 1/10 degree model. We have this topography spectrum from Goff, and we also have the ID mix, which describe the ambient wave field, or the GM part of the wave field. And then you have turbulence and mixing, but also the wave stress. This is here a map of the flux at the bottom. And the global integral is 0.3 terawatts. And the right figure shows here the interior energy transfer. But that's actually the modulus of the interior energy transfer. And just to show you that it's not zero, actually it's maybe as large as the bottom flux as the interior energy exchange, but only if you take the modulus. If you integrate it really, then it's very small actually. It's averaging out between plus and minus. So it's in the average, it's zero, almost zero. And the flux is large in the Southern Ocean, and the Atlantic Pacific is surprisingly low, this Lee wave energy flux. This is the stress at the bottom on the right by the Lee waves in the model. And here on the right, the surface wind stress forcing the model. And you see in the Southern Ocean and Atlantic, the magnitude of the flux of the stress at the bottom is as large as the stress at the surface. And it gets even larger actually. This is here a figure showing the flux distribution over the vertical, and it's decaying, of course, with the vertical, but at some places here, it's reaching this, the surface, into the surface layers. And that's now our task to analyze this in detail, how the flux looks like and distributes over the vertical. And maybe we can approximate the decay scale with a simpler model. So then I can come to my summary. We have an analytically consistent Lee wave closure, which is based as the normal ID mix on the radiative transfer equation. We have assumed horizontal homogeneity, but this is possible to relax, but we think it's not so relevant. So at the moment, we have a model without it. More relevant are maybe the closures for the nonlinear terms on the right-hand side, the S terms. And there's nonlinear interaction within the Lee wave field, which we need to put in. There's nonlinear interaction, wave-wave interaction with the ambient wave field, with the GM background spectrum. Maybe also nonlinear scattering at topography. What we do have is the interaction with the mean flow, at least. Then these estimate in the global model yield a bottom flux of 0.3 terawatts, consistent with the previous estimates, somehow in the middle. And the Lee wave stress at the bottom on the large-scale circulation can be large, actually. What it didn't show is that it's actually due to the mesoscale eddies, not to the mean flow, this flux, but due to the mesoscale eddies, both the stress and the flux. So you need an eddying model to put this in, or parameterization for an eddy for the eddies. And what I also didn't show is that the ID mix simulation of the GM background field compares much better with observations like the Argo floats, including the Lee wave forcing, than without the Lee wave forcing. So we need the Lee waves to improve the ID mix model. And the problem is that we still need to include in this model, of course, other means of dissipation of the eddies. And what we, of course, use is the biharmonic friction operator, which we want to get rid of. And there are these possible candidates, but at the moment, we still have biharmonic dissipation, so it's not analytically consistent. This is where we are working on currently. Thank you very much.
Okay, we have a minute of questions, but I don't see any questions in the chat, at least. Any questions to Carsten?
There's some raised hands, I think.
Oh, okay, Kevin.
So Carsten, is this based on like a steady current, or like, can you take into account time varying bottom currents, say tides, Rossby waves, well, the eddies themselves?
Yeah, no problem. Although in principle, you assume that the U is not time dependent in the theory, but then in the model, we ignore that, of course.
Sure. Okay, but would there be cases where you think that the time dependence of the current is important?
Well, I don't know. Yeah, for tides, it's definitely important because that's what the tides do, right? They oscillate. For the mesoscale eddies, the time scale is much larger, right?
Yeah.
And so it wouldn't be so important.
Ulrich also has a question.
Yeah, I'd just like to check in the atmospheric context. It's known that mountain waves can only be calculated with some limited accuracy from the linear boundary condition for at least two reasons. One being that the flow is not necessarily passing over the mountains, but also around the mountains, which is called blocking in the atmospheric parameterizations. And another thing is that also the turbulence, which might also be generated by flow over mountains, can then take away some of the energy and limit the effective height of the mountains. So have you looked at how this compares to wave and highly resolving simulations of the process? Or is this no issue in the ocean?
No, it's an issue, and but it's an issue of the bottom boundary condition for the energy flux going into the Lee wave field, right? And what we have is this kind of a simple closure with which other people also have. Actually, it's kind of a function of the Froude number, if I remember correctly. So you have a limiter. If the Froude number gets too large, then you limit the flux due to these processes which you have described. If the flow gets too strong, it goes or no, if it's too weak, it goes along, not across the topographic obstacle, but beside it somehow this way. And we just took from the shelf what they did, and that was partly validated in high resolution wave resolving models, partly just empirical formulas or fudge factors. But I think that's only for the flux, actually. Only matters for the flux, not for the distribution of the energy over the vertical, which we are more interested in. But we are also currently looking at this, how this function, this limiter, affects the solution, of course.
Thanks.
All right, thank you, Carsten. We can move on to the next talk by Wenjing Dong. Are you there, Wenjing? Okay, great. And the talk is going to be about stationary inertial gravity wave frequency spectra generated by geostrophic mean flow refraction.
You have to unmute yourself.
Sorry. My name is Wenjing. I'm a PhD student at New York University. I'm going to show some work I'm doing with my advisors Oliver Buehler and Schaefer Smith. Inertial gravity wave is everywhere in the ocean, and they tend to have a wave continuum called Gary-Mann spectrum. Many observations have confirmed the existence of this wave continuum, and they show a good agreement with Gary-Mann spectrum. On the left, I'm showing a figure from Morin data. Here you can see there is a wave continuum that has a slope about -2.25. There have been some theories proposed to explain the existence of this wave continuum, including weak wave interaction between waves, and tides interaction between waves and mean flows. Recently, a numerical study by Barkin Winters and Michael Williams 2017 provides evidence for the idea of interaction between mean flows and the waves. In their paper, they have three different simulations. In the first simulation, they force their flow with steady zonal wind stress that drives zonal mean flow, and Eichmann pumping, Eichmann circulation then tunes isopignals and generates baroclinic instability that forms mesoscale and sub-mesoscale eddies, but inertial waves are not generated. They have in the second simulation that is not shown on this figure. They force the simulation with high frequency zonal wind that has zero mean, so that's going to excite inertial waves. In their third simulation, they combine these two forcings and they plot the horizontal energy spectrum as a function of frequency. On this top figure, you can see that when there is only wind stress forcing, the energy slope is quite steep, and there is no peak at initial frequency because initial waves are not excited. In their high frequency forcing simulation, there is this initial peak, but again, the spectrum is very steep for high frequency. What is interesting is that when they combine these two forcings, you can see this spectrum matches the GM spectrum really well. So this comparison shows that the interaction between mean flows and waves is important to the formation of GM spectrum. This is the motivation of our work. We would like to understand the interaction between mean flows and waves in an idealized setup. To do that, we use the WKP approximation. We would focus on the statistics of inertial gravity waves, in particular the intrinsic frequency. We have a geostrophic mean flow. The vertical velocity is 0. By neglecting nonlinear interaction between waves, we have a linear equation for the action density. And this equation can be solved by the Euro retracing approach by solving equation for x and k. Along each ray, the action density is conserved because the energy density is the product of action density and intrinsic frequency. If intrinsic frequency changes, the energy of wave will also change. So by tracking the intrinsic frequency, we can track the energy exchange between mean flow and the waves. However, for steady flows, there is a conserved quantity. The absolute frequency is conserved. So if the change of absolute frequency is, most of the change is accounted by the change of intrinsic frequency, that means the intrinsic frequency cannot change much. And actually, that's the case in two-dimensional flow. If we consider the inertial gravity waves in shallow water system, we have a dispersion relationship that depends on the magnitude of the wave vector. And you can show that for small Rossby numbers, intrinsic frequency can change only a small amount for steady flows. Here I'm showing a plot from our recent work. Here we plot the trajectories of wave vector in spectral space. Initially, those waves are located on the black ring. For steady mean flows, they spread a little, but they remain confined in spectral space. And so the frequency, intrinsic frequency is also confined. But if we have unsteady mean flows, the wave vector can travel far away from their initial location. So the frequency can spread. So that's the story in two-dimensional case. If we look at the three-dimensional case, the story will be different because we have a different dispersion relationship. the intrinsic frequency does not depend on the magnitude of the wave vector. It only depends on the ratio of horizontal wave number to the vertical wave number. According to the wave capture theory by Buehler and McIntyre 2005, for steady flows, wave number can grow exponentially, and eventually the ratio of horizontal wave number to vertical wave number is proportional to the length aspect ratio of the mean flow, h divided by l. So the intrinsic frequency of the wave will also be determined by the mean flow. However, in this theory, it is assumed that the velocity, the shear, background shear is approximately uniform in space. So in this talk, we are going to consider random mean flows that's spatially homogeneous and stationary in time. In this talk, I'm going to show the results for steady mean flows only. This is a realization of a stream function. The length scale of the stream function is around the deformation scale, and we realize the velocity field on a periodic domain. So to examine the spreading of frequency, we just put some waves in the ray tracing simulation and let the intrinsic frequency be the same for all the waves. So waves are located on a cone, and for convenience, we just let the vertical wave number be same for all waves. So this is their initial location in spectral space. This is initial location in physical space. Initially, we are interested in quantifying the spreading of frequency and how and investigating how the average the frequency change. However, we found a stationary energy spectrum will form. So on the left, we have time evolution of energy density for simulation with the initial intrinsic frequency is 5F. This point. Gradually, the peak at this point decreases, and the spectrum is converging to a stationary spectrum. For this simulation, it takes around 100 days to reach the steady state, stationary state. If we start with different initial frequency, here we have 3 different initial intrinsic frequency. We see that eventually we end up with the same energy spectrum, and the energy spectrum approximately is the power law of intrinsic frequency. Since the waves are modified by the mean flow, the stationary spectrum must be shaped by the mean flow. So we are interested in how what the properties of the mean flow shaped the stationary spectrum. What we did is we look at the eigenvalues and eigenvectors of the this matrix. Because if we look at the evolution of wave vector and assume x does not change, this is just a linear equation for wave vector, and the eigenvalues and eigenvectors of this matrix determine the behavior of wave vector. For this matrix, we have 3 eigenvalues. 0 is due because the vertical velocity is 0, and we have 2 other eigenvalues determined by the Occam-Weiss parameter. If for positive eigenvalue, its eigenvector will grow exponentially. For imaginary eigenvalue, its eigenvectors will oscillate in time. if we compute the eigenvalue for every grid point of our velocity field, we get a distribution of this with parameter, and turns out that it's more likely to have real eigenvalues than imaginary eigenvalues. If we collect all the real positive eigenvalues and compute intrinsic frequency using growing eigenvectors, and we can create a PDF frequency by multiplying by intrinsic frequency. We get energy spectrum. We can compare that with the energy spectrum from retracing simulations. It turns out these two have a similar shape, and for the frequency between 2f and 10f, they match well, but for low frequency and high frequency, there are some differences. As I mentioned previously, the spectrum is approximately a power law of intrinsic frequency. So we investigate what determines the slope of the energy spectrum. Here, I'm showing the plot of slope of energy spectrum as a function of aspect ratio of the mean flow. And these dots are the data obtained from retracing simulations. These data can be fitted by a straight line really well. Here we have a log scale for aspect ratio, but we have linear scale for the slope. In the ocean, the aspect ratio of the mean flow is around 10 to the minus 2, and for this range of value, we have a slope that is around -2.
You have 2 minutes left.
Okay. So previously, I have only shown results for mean flows consisting of single vertical mode. On this slide, I'm showing the results for mean flows that consisting of multiple vertical modes that is built according to Chinese 1971 geostrophic turbulence model. Here again, although we start with different initial frequency, we end up with same stationary spectrum. To summarize, we have found by running retracing simulations, stationary energy spectrum will form irrespective of initial frequencies, and this energy spectrum can be approximated by the energy spectrum obtained using the growing eigenvectors of shear tensor. The energy spectrum is approximately a power law of intrinsic frequency, and the slope depends on the aspect ratio of the mean flow. As the next step, we are going to use QG flows from direct numerical simulations as mean flows. Thank you for listening.
I see Jacques has a question.
Okay.
Yes. Just to clarify, while your frequency spectrum goes to a stationary setup, the wave number spectrum is always changing, I guess.
We look at the wave number spectrum. There seems to be a steady state, but it takes much longer to reach that steady state than the intrinsic frequency spectrum.
And what would lead to that steady state? You don't have a cascade to smaller and smaller scales continuing?
Yeah, I'm not sure what is this stationary wave number spectrum. Initially, we also expect that's going the wave number will continue growing, but it seems there is a stationary spectrum. because it takes much longer, and so we don't have like many results for that spectrum.
And can I ask, once you reach the stationary spectrum for the frequency,
yeah.
Is the intrinsic frequency much smaller than the Doppler shift? I mean, is it a sort of wave capture scenario?
Oh, once we reach the steady state, the group velocity of the intrinsic group velocity is much smaller than the mean flow. So I think it's approximately in the wave capture regime.
Right, okay, thanks.
Okay, Hussein.
Yes. Very nice talk, Wenjing. Thank you. Just a quick question. So you were also hinting that probably you can explain the frequency spectrum in the ocean, but as the frequency spectra shows, like the waves are really high amplitude, and they peak at F and then tight frequency. And in your theory, there is no wave feedback on the flow. The mean flow is not affected by the waves. Do you think you can still, your theory still has implication and like an explanation for observation without taking this wave feedback into account?
I think it probably depends on what the length scale, time scale we're looking at. I think probably the low frequency part probably affect the mean flow more than the high frequency. And for our results, I think it's probably if we consider the feedback of wave to the mean flow, probably the results at a low frequency near F will be changed.
Thank you.
Okay, any more questions within Zoom? I don't see any more raised hands. There's a comment on YouTube by Eric Kunzo. I wonder if the heterogeneity of the QG eddy field in the global ocean is reflected in variations in internal wave frequency spectral slope. But this is answered by Schaefer-Smith already on YouTube, unless Wenjing, you want to say something to that?
Oh, I don't have anything to say.
Pardon me?
Oh, I don't want to comment.
Cool. Okay, but we are also closing on the time. So thank you, and we can move on to the next talk by Cynthia on Lee waves and shear flow. Are you ready?
Yes. Let me share my screen right now.
Okay, great.
Okay. Let me make it full screen. Is it full screen?
Yes.
It seems like rehearsal. Let me play. Okay, thanks. So yeah, thanks for having me. My name is Yue Cynthia Wu from Woods Hole Oceanographic Institution. So today I'll talk about Lee waves in shear flow. This work is in collaboration with Dr. Amla Mahadevan from Woods Hole, Eric Kunze from Northwest Research Associates, and Ami Tandon from University of Massachusetts Dartmouth. And this project is funded by National Science Foundation. So first, the motivation. Roughly 1 terawatt of wind work drives the ocean circulation. But how this amount of power is dissipated for the ocean circulation to remain a steady state is still uncertain. Some suggested pathway to dissipation includes the bottom drag, which accounts for less than 25% of the 1 terawatt wind cliff, the interior loss of balance, and the surface instabilities accounts for a smaller fraction. And the largest energy sink is through Lee wave generation, which accounts for 15 to 75% of the global 1 terawatt input. So Lee waves are generated by geostrophic front interacting with the bottom topography. And from a traditional view of the ocean energy cascade, that this amount of Lee wave energy is eventually lost into small-scale turbulence due to wave breaking. However, recent measurements in the Southern Ocean find that turbulent dissipation rates associated with Lee wave breaking for short-haul predictions by as much as 1 order of magnitude, which suggests turbulence suppression. So, for example, in the Southern Ocean, the Antarctic circumpolar current has several deep-reaching jets that are actively interacting with the topography and generating Lee waves. However, the measured turbulent dissipation rates at these locations is surprisingly low when compared to either the linear Lee wave theory or to the observed Lee wave energy flux. So it seems like turbulent dissipation is only one fraction of the predicted Lee wave energy flux. And now the question becomes, where does the remaining energy go? And is there another mechanism for Lee waves to lose their energy? So we will focus on this question in this talk. So for Lee waves, they have an intrinsic frequency equals the topographic wave number K dot with the front velocity big U. And after a Doppler shift, their Eulerian frequency in a fixed reference frame is 0, indicating that Lee waves are stationary in reference to the topography. And for a general form of internal gravity waves, they exist in the frequency band between the Coriolis frequency F and the buoyancy frequency N. So for Lee waves, they are trapped within the geostrophic front where their intrinsic frequency is between F and U, and they are evanescent outside of the front when big U is 0. So this indicates that Lee waves must be dissipated locally near their generation site, and remote dissipation cannot explain the discrepancy between the Lee wave energy flux and the turbulent dissipation rates. From the concept of wave action conservation, we know that along the group velocities of internal wave propagation, wave action is conserved rather than wave energy. And although the theory of wave-mean interaction tells us that internal waves and the mean field can exchange momentum and energy through Reynolds stress and mean shear. So here our hypothesis is that another fraction of Lee wave energy will be used to exchange with the mean field, that is the geostrophic front. So actually this idea has been well explored in atmospheric studies, where the effect of mountain waves on the background wind has been parameterized into one quantity known as the gravity wave drag. However, in the context of the ocean, since the ocean has a free surface that can reflect internal waves, the effect of incident and reflected waves will cancel since they travel across the shear in opposite directions. So that as illustrated in scenario A, for a free propagating internal waves, the net contribution of the internal waves on the background shear flow is trivial. But this is not always true for Lee waves. In scenario B, we consider a bottom intensified flow. So Lee waves are generated in the bottom ocean and propagate upward. At some location, when the Lee wave intrinsic frequency decreases and approach the Coriolis frequency, which is the lower bound of the internal wave band, Lee waves encounter their critical layers, and their vertical wave number estimated from the dispersion relation goes to infinity. So that's where Lie waves are driven into smaller and smaller scale in the vertical, and they eventually break into 3D turbulence. So in this scenario, there is no reflection by the free surface, and thus the net effect of Lie waves on the background flow is non-trivial. Okay. To study the energy exchange between Lie waves and the mean flow, we set up an idealized numerical model using the process steady ocean model. Here, we initialize a 3D domain where the x-axis is the zonal direction pointing to the east, the y-axis is the meridional direction pointing to the north, and the z is upward. So the topography we have been using is very simple. It's a two-dimensional topography as a sinusoidal function of the zonal direction. And for simplicity, we have been using a single wave number where the zonal wave number of the topography is 1.2 kilometers. And the topographic height is 10 meters in the vertical. So this is considered subcritical or mild in order to avoid topographic blocking or other nonlinear effects. We initialize the stratified fluid in this domain by sloped isopycnals. So according to the thermal wind balance, our initial condition for the geostrophic front is a bottom intensified and laterally confined flow. So given this initial condition for the geostrophic front, we can roughly estimate the vertical wavelengths for Lie waves using the dispersion relation for inertial gravity waves. So as in the right panel, you can see that the Lie wave vertical wavelength is decreasing as the front velocity decreases. At locations where k dot u approaches f, the vertical wavelength shrinks down to tens of meters in the vertical, which is comparable to our vertical grid size of the numerical model. So that's where Lie waves encounter their critical layers, and they are driven to very small scale in the vertical. Now let's have a look at the simulation results. So we run this simulation up to 20 days, and the upper two panels are for the zonal velocity, and lower two panels are for the, the upper two panels are for the vertical velocity, and the zonal two panels are for the zonal velocity perturbation that associated with Lie waves. As you can see that Lie waves are trapped within the geostrophic front below their critical layers, and they never escape to the upper ocean or close to the lateral boundaries. And at locations where k dot u approaches f, we find shrinking vertical wavelengths of the vertical velocities and in the zonal velocity perturbation. And also the vertical velocity profile shows that near the critical layers at roughly 1,000 meter depths, the horizontal Lie wave velocities is amplified. So due to the shrinking vertical wavelengths and amplified horizontal velocity, shear is dramatically increased near the critical layers. So shear is defined as the vertical gradient of the horizontal velocities. So when shear exceeds its critical value of 2 times the buoyancy frequency, we would expect shear instabilities will happen. And
the plots that you have for vertical velocity and zonal velocity, actually it's not visible. Is it an animation?
Oh.
Yeah,
oh, there are movies, but I'm sorry for that. Yeah, I don't know.
Just to let you know that, yeah.
So if this show up.
Yeah, it does, yeah.
Okay, maybe something wrong with the sharing, but yeah. So when shear instabilities are developed, we expect the turbulent mixing will dramatically increase near the critical layers. Yeah, I'm really sorry for the movies. So we can take a brief glance at the movies here. Okay. And then we revisit the decompose the energy equations. So in the analysis, we write the total velocity and buoyancy fields into three components. The mean component associated with the geostrophic front, the wave component for Lee waves, and perturbations that are the residuals. So we worked out the decomposed energy equations for the mean field and for the internal wave field respectively. In the mean energy equation here, MKE and MAPE are the mean kinetic energy and mean available potential energy. And in the internal wave energy equation, we have on the left-hand side, that's the total derivative of internal wave kinetic energy plus internal wave available potential energy. And on the right-hand side, we have all the terms that can affect the total time derivative of the energies. So among these terms, we can identify the exchange term, which is expressed as the momentum flux times the mean shear plus the buoyancy flux times the mean buoyancy gradients. So this term appears in both the mean and the internal wave energy equations, but with opposite signs. So they represent the amount of energy being exchanged between the mean fields and the internal wave fields. Okay, so to look into the energy budget for the mean field associated with the geostrophic front and for the internal waves, first we show the mean energy budget. I put the mean energy equation here again and plot each term as a function of depth in each panel. So the first panel shows the transport term, which is the amount of mean energy redistributed by wave fluctuations. The second term is the exchange term, and we recognize that the dominant component is the solid red curve, which is the vertical momentum flux times the vertical shear.
You have 2 minutes left.
Yeah. And then we sum up all the components in the exchange term. We find that the exchange term is always positive below the critical layers. That indicates that the mean field is actually receiving energy from Lee waves. And then we sum up all the right-hand side of the energy equation and plot the net energy budget as a function of depth. And we find very good closure at all depths except in the critical layers and near the bottom topography. And similarly, I plot the wave energy budget. And here, the exchange term is negative below critical layers, indicates that Lee waves are losing energy into the mean field. Or in other words, the mean field, the Lee wave energy has been reabsorbed into the mean field. If we compare the exchange term to the pressure work, which is also known as the Lee wave energy flux, we find that roughly 70% of the Lee wave energy flux is actually being reabsorbed. And compared to the dissipation of Lee waves, only 15% of the Lee wave energy flux is dissipated. Again, I show the net wave energy budget in the last panel, and we find the energy closure for Lee waves is quite decent, except we have a positive net value near the critical layers. Due to the limited time, I won't dive into the details, but the conclusion is that this excessive amount of energy is actually being used for the generation of near inertial waves. So the discovery of energy exchange between geostrophic front and Lee waves, and also the discovery of the spontaneous generation of near inertial waves sort of completes our hypothesis. From the traditional view that energy can only go from large scale to small scale and eventually dissipate, it was believed that 15 to 75% of the 1 terawatt wind input has been dissipated through Lee waves. But this is based on the assumption that 100% of Lee wave energy flux is lost into turbulent dissipation. However, in our research, we find that a significant fraction of Lee wave energy can be used to exchange with the geostrophic front, and a smaller fraction of energy can be used for the generation of near inertial waves when shear instabilities is developed. And only a small fraction can be used for dissipation. So just a brief conclusion that an idealized numerical model of Lee waves in shear flow is conducted, and we found in the scenario of a bottom intensified flow, the effect of reabsorption of Lee wave energy into the background shear flow is order 1. And also, Lee waves may not be as efficient as they were thought to be as a pathway to dissipation for the ocean circulation. So we have to put a question mark in the percentage of the energy being dissipated through Lee waves. So that concludes my talk. And questions and feedbacks are very welcome.
Questions for Cynthia? I don't see any raised hands. Okay, Kevin has a question.
Hi, that was a very interesting talk. So a couple of questions. On one of your slides, you mentioned, was it 70% of the energy is reabsorbed and 15% is dissipated? So I'm wondering what happened to the other 15% of the energy. And yeah, I think that, yeah, on this slide. And I'm also wondering, so the energy that's absorbed, does it create shear layers that could potentially be unstable and then lead to further dissipation?
Yeah, to answer your first question, so as we show in the plot, actually we observe the first term that is the transport. So this term has a significant negative value. So this is actually the amount of internal wave energy being redistributed by wave themselves. So this could contribute a significant percentage of the energy flux. And also, we calculated, so we obtained a small positive net in the wave energy budget. So this is actually due to energy going into the spontaneous generation of near inertial waves near the critical layers. I think this amount of excessive energy could also account for the remaining 15% of the Lee wave energy flux. Your second question is how does Lee waves modulate the mean shear and whether it leads to additional dissipation? Am I understanding it right? Yes. Yeah, so in this research, we have been using a restoration to preserve the mean front of the mean field for the geostrophic front. I'm not sure whether I showed that slide or not. But the idea was that if we consider the geostrophic front and Lee waves as one system, so due to dissipation, if we run this numerical model without any external forcing, both the geostrophic front and Lee waves will gradually spin down. And that's why we add a restoration to preserve the large-scale geostrophic front. So that prevents Lee waves modify the mean shear in the geostrophic front. But I think that's an interesting question. Without restoration, I believe Lee waves will have an impact on the mean shear, and that may be worth to looking into.
Thank you.
Okay, Boris also has a question. Boris?
Yes, it's a simple, short question. Interesting presentation, thank you. Just wanted to ask you if you consider dissipation in the horizontal and vertical separately, or you think they are the same? And if they are separate, if they're different, can you give me the numbers to appraise the dissipation processes in the horizontal and in the vertical? Also, I would like to notice that the dissipation is not always related to the energy flux. Just a side note.
Okay, so for the values of the viscosity we have been using is that in the horizontal, we have been using a Laplacian mixing where the, so this number is corresponding to the grid size of 100 meters in the horizontal. And that's equivalent, in the horizontal, we have been using a biharmonic mixing in the horizontal. So this is the advantage of a biharmonic mixing is that it can preserve the mean field as much as they can, but damp the small scale internal waves just as usual. And in the vertical, we have been using the traditional Laplacian mixing. So this is the value of the vertical viscosity. So this is this number 4 times 10 to the minus 3 is actually quite large, but since there is a critical layer in our numerical model where Lee waves are driven into very small scale. So by using a large vertical viscosity that avoid any variance or instabilities to develop. And also this value 10 to the minus 3 is quite realistic, for example, in allocations through the Drake Passage and through straits, where vertical mixing due to internal waves are significant.
Yeah,
so,
I understand. But this is viscosities. I asked you not about viscosities, but about the dissipation rate or energy flux.
Oh, dissipation.
If you assume, say, Richardson relationship between viscosity and fluxes, can you estimate the fluxes?
Yeah, actually, we are running out of time. So perhaps you could continue the discussion later in Gathertown or during the discussion. Is that okay?
Sure.
Or in the chat.
Yeah,
and
sure.
Cynthia, there was a question.
I'll keep in touch.
Yeah, there was a question for you in the live chat too, and I've put it in the chat so you can address it there and you can continue there. All right, thank you. And we can move to the next talk by Chris Holland on shear-induced breaking of internal gravity waves. Chris, are you ready? Okay, you started sharing.
Okay, and can you hear me?
Yes.
And you can see the slides?
Yes, it's visible.
Okay, good. Right. Hello, everyone. I'm Chris. I'm currently a postdoc at the University of Twente in the Physics of Fluids group, but I'm going to talk today about some work I did as part of my PhD at the University of Cambridge with John Taylor and Colin Caulfield that was funded by the UK Natural Environment Research Council on the shear-induced breaking of internal gravity waves, which might sound similar to some of the talks we've just heard, and it's been very nice to have a couple of relevant topics introduced by other speakers. But I'm going to take you quite far down in scale. So I noticed that Cynthia was using a grid resolution of about 8 meters in the vertical. My domain size will be of similar magnitude. So I'm going to look at the fundamentals of the wave breaking events as they go to turbulence and the relevant scales for that. Okay, so I'm going to present some very idealized work based on some numerical simulations, but let's start with the kind of things we're motivated by in terms of observations. So this is a study from 2000 by Alfred and Pinkel in JPO. You can see I'm looking at depths on the scale of 5 to 10 meters. So in this plot, we have black lines denoting isopycnals, surfaces of constant density. Black dots represent local density overturns, where we expect significant turbulence and mixing. And the color scale denotes the Richardson number. So what we can see is that there's overturns located in a range of different scenarios. So in the top case, you see we have low Richardson numbers associated with high shear, and you can see that's the dominant process there. But on in the other pictures, there's a lot of motion of the isopycnals that the authors attribute to internal wave strain. And you can see as the sort of contours of Richardson number appear, the shear and the wave sort of appear to be on a similar vertical scale. So maybe the shear is associated with some near inertial wave, a local vortex or something, but there is shear and what seems to be an internal gravity wave on similar vertical scales. So what I'm interested in is understanding, okay, what are when you have these two factors on a similar scale, what are the relevant braking mechanisms, say in this case, when it's not just a unstable shear flow giving you a standard shear instability, and what does this mean in terms of vertical or diapycnal mixing? So large amplitude internal waves can be susceptible to a range of instabilities, including the parametric instabilities you see at sort of lower amplitudes. But as you get to large amplitude, you can also see convective instability when the wave is sufficiently large that it locally induces these density overturns, even as the wave keeps its structure, and shear instability too. And these are slightly misaligned if you think about how the polarization of the wave works. And so what I'm going to define is a wave steepness as a dimensionless amplitude of the wave, such that if the wave steepness is greater than 1, then you have some statically unstable region in the density field. And why this is important is that convective flows are typically associated with more efficient mixing than shear instability. So if you think, oh, my wave is primarily breaking down due to convective flows, then perhaps the mixing will be more efficient, and we need to account for this if you're, say, inferring your mixing from your TKE dissipation rate. So what I'm going to do is come up with a very, very simple setup for a numerical simulation and study the breaking of a large amplitude plane wave in a mean shear flow on these small scales where the shear is on a similar scale to the wave. So as I said a couple of times now, I'm on very small scales. So I'm going to be neglecting rotation in this problem. I'm also thinking about this sort of turbulent event, and we think that on these sort of short time scales, as well as the length scales we're looking at, it's more important to factor in the stratification than the rotation. So I'm just going to consider a triply periodic domain that's going to be this shape. I can get into that in a minute. And we're going to have a mean imposed stratification. So we have a background uniform buoyancy gradient, and we solve perturbations to that. And I'm just going to consider a simple initial value problem of this sinusoidal shear and superpose a plane internal gravity wave on it. Okay, so this is just illustrating the point that our buoyancy will increase with height, but we're solving for a periodic perturbation to that. So even the horizontally average mean doesn't have to be uniform. It's just that we have some mean stratification over the poles. So here's the simulation setup in terms of buoyancy contours, the horizontal velocity, and the vertical velocity. So we're just adding this sine profile to an internal wave. I'm considering a wave of this aspect ratio. So we have 1 horizontal wavelength in the box and 3 vertical wavelengths in the box. This wave is chosen primarily because it matches roughly with an estimate from the observations I mentioned earlier, but also it's not unstable to parametric subharmonic instability. So our domain is, as I said, it's 1 horizontal wavelength in the x direction, and we also have a thin third dimension because the flow is initially 2D, but we want to allow the development of 3-dimensional turbulence in this case. And for the parameters we're picking, the effective domain size is still quite small, so a height of about 8 meters. And you can see we consider a couple of different wave steepnesses, and this is illustrating when s equals 1, you have your buoyancy contours almost overturning. So I'm going to show now a flow visualization for the case of Reynolds number 8000 and a wave steepness of 1. At the top, we have the vorticity field, both in the plane of the initial wave, and this is the cut through the spanwise direction, and we also have the buoyancy field at the bottom. So here you can see the movie playing. You get some intensification towards the middle, the development of turbulence, and then slow decay from the turbulent state. Don't worry if the movie was a bit blocky. I will show some snapshots from that now. So this is from time t equals 0, just the initial condition. You can see there's some focusing of this negative shear essentially towards the middle, and some distortion of what looks to be the wave field, and some overturning buoyancy contours already in the same part of the domain. You can see now that there's some smaller scales emerging on the flow, and we can also see some 3-dimensionality that appears, that seems to be coinciding with these regions of static instability, suggesting some convective behavior. And then turbulence seems to sweep the domain, and we see that the region that was previously dark green and sort of a strong negative vorticity is sort of breaking down into this nice patch of eddies, well, vortices, I suppose. And then at later times, you can see this sort of organization of the flow into these structures that are somewhat reminiscent of what you see when you get a Kelvin-Helmholtz-like billow. So just to recap that, we can see we've got some sort of wave refraction going on, what looks to be convective instabilities and some Kelvin-Helmholtz-like billow structures. But that's all well and good, sort of looking at a movie saying, oh, we think this is what's happening. Can we sort of provide a bit more evidence for this? And what does this mean for the mixing associated with this event? So as a lot of the previous talks have highlighted, classical ray tracing for a steady shear flow tells you how, as a wave propagates through a sort of larger scale shear flow, how does the local horizontal and vertical wave number change? So this isn't really appropriate for our setup because we don't have the scale separation. Our wave is in extremely large amplitude. But if you just think about the idea, we start with a wave that's initially positive horizontal wave number. So if you think about the evolution of the vertical wave number, according to this equation, we'll get high values of m where we have negative shear. And that's essentially, in some sense, what we're seeing. We're seeing some the wave that was initially sort of a uniform wave number. In the vertical, we see sort of these small scales emerging in the middle of the domain where there's this negative shear. So based on this, we can be a bit rash and say, okay, well, what if we just do some ray tracing? So we're going to solve the ray equations for our mean flow u of z. That's just going to be taken to be our initial sine profile, and follow the rays. Now, based on our initial condition, the extrinsic frequency is going to vary with height because depending on where you are, the intrinsic frequency based on the aspect ratio is the same, but the Doppler shift will depend on where you are in the shear flow. So we get a range of different rays. The rays cross. It's very difficult to interpret in terms of our initial superposition. But what we see is that you get a lot of rays accumulating towards the middle of the domain. And these are predicted critical layers for some of these rays. And that's all well and good. Okay, you can say, yes, there's some energy focusing towards the middle, and then your waves will increase in amplitude and break through some nonlinear process. But what's kind of remarkable is that if you plot some, so this is a space-time plot of the...
You have 2 minutes left.
That's okay. So this is a space-time plot of the horizontally averaged buoyancy flux that just gives you some idea of some property of the waves and the turbulence. And you can see for these cases that start with lower initial wave steepness, we have these structures that seem to follow this shape very closely. And it's kind of remarkable how this linear theory gives you something vaguely reminiscent of what's going on in the simulation, when there's a lot of approximations that are not holding. So in terms of these waves actually breaking down later, how can we justify what we're seeing? So we can think about the convective breakdown being related to a local Rayleigh number. When we get a density inversion, we can think about what's the buoyancy jump in this statically unstable region, what's the height difference, and when we compute this Rayleigh number, so these are energy time series, and what you should look at is this bottom plot, which is the fraction of span-wise turbulent kinetic energy, and we see a exponential increase, so this is a log scale, in the span-wise velocity component of the TKE once this Rayleigh number exceeds order 1,000. So this is just the maximum number, Rayleigh number in the domain. So you see highly suggestive behavior related to a linear instability of making these convective rolls. And finally, what does this mean for mixing? So we said things look vaguely Kelvin-Helmholtz-like in terms of the structures you get at later times. And you can even relate this in terms of the width of this shear layer that is changing with time. So take this with a pinch of salt, but we have an appropriately sized structure given the earlier size of the shear layer. But what's really sort of important is if you compare the dissipation rate of APE to the dissipation rate of the TKE, the turbulent kinetic energy and the available potential energy, and come up with a mixing efficiency, comparing to all these different kinds of flows, we, over the course of the event, we're getting a mixing efficiency and this sort of bursting profile that's most similar to what you see from Kelvin-Helmholtz instability simulations in a stratified shear layer. So just to conclude, we see convective instabilities first introduce the three-dimensional motion in this system, but the majority of the mixing and turbulence is more reminiscent of what you see in a Kelvin-Helmholtz-like DNS, and the rash application of ray tracing is somewhat consistent with the aspects of the DNS. So I'll just leave up some open questions, and I can talk about these more if people want me to. So thank you.
Yeah, there are 3 minutes for questions. No raised hands. Are there questions on the live chat? All right, since we are over time anyway, let's have a break now instead. And any questions to Chris, please ask him during the discussion, during the break, or in Gather Town. Thank you, Chris, and thank you all the speakers for this session. Remember that today, at the end of the day, we have the group photo. So everyone, most of you, please try to be on Zoom so we can make a group photo later. And since many of you cannot experience Hamburg in the same way as in person, so we thought of bringing a bit of Hamburg to you, some impressions of Hamburg. So I've prepared a little slideshow from the pictures that I've taken of Hamburg, and I will just share it here so you can have a look at them during the break.
So Manita, what time are we going to resume?
Yeah, so maybe we say, yeah, now we are maybe 5-minute break from now. So 5 p.m. we can start again.
Okay.
Yeah.
So do we start again, Kevin?
Sure. I'm here. So is Aurelian here?
I am here, yes.
Okay, well, I guess we can get going with our first speaker of the last session before the photographs. So go ahead, Aurelian.
Hi, everyone. So can you see my screen?
Yes, that's good.
Perfect. So thank you. Thanks to the organizers. This has been a very interesting meeting so far. And so my presentation is slightly different, I think, from all the other ones that I've seen so far. For one reason is that I'm focusing on the atmosphere, and the other thing is that I will mainly be talking about observations and diagnosing near inertial waves in the lower stratosphere from superpressure balloon observation and ECMWF reanalysis. So this has been explained a few times already in this meeting, but just a reminder, the gravity wave frequency spectrum that can be inferred from oceanic observation has a clear structure. If you go from low frequency to high frequency, you encounter first a spectral gap, as shown here in this power spectral density of the U and V current. And then you go to the Coriolis frequency, where you encounter a peak. And at higher frequencies, you have log-log linearity, so self-similarity of the gravity wave spectrum with tidal resonance. And so in the ocean, the mean current, the background current is usually small, but it's not the case in the atmosphere, where the large-scale background wind is very large in magnitude, and so Doppler shift is important. So we have seen yesterday in Spencer Jones' talk that Doppler shift also can have an impact in the ocean, but in the atmosphere, I would argue it's much larger. So I'm just taking here an example similar to the one that was taken yesterday, but with typical value for the atmosphere. If you take a background wind of the order of 10 meters per second, a wavelength of 500 kilometers, and you end up with a Doppler shift of the order of the Coriolis parameter. So this is really messing around with this pretty picture. So what has been done to diagnose inertial waves, or what can be done in the atmosphere? There are several approaches that can be taken. One of them is to use indirect diagnostic and make use, for instance, of the polarization relations. And this, for instance, with vertical profiles, radar observations. This is called the hodograph method, which consists in plotting V as a function of U. And if you have near inertial waves, you should get something like a circle when you plot V as a function of U. But this is indirect. This relies on the polarization relation. Another more direct way, which is what I'm going to talk about, is to use Lagrangian platforms for observations. And the only Lagrangian platforms that I know of in the atmosphere are superpressure balloons, or SPB, in the rest of the talk. So you have a couple of pictures of those balloons, one here that has just been launched, and two here that are on the ground but fully inflated, just to show you what they look like. Those balloons have a rigid envelope, which means once they reach their equilibrium level, or they have an equilibrium level in the atmosphere, which is a constant density surface, usually 0.1 kilogram per cubic meter. And once they reached that equilibrium, they basically drift horizontally following the flow. That's why we often term those observations quasi-Lagrangian, because they follow the horizontal flow and they give you access to the intrinsic frequency. And so usually superpressure balloon observations can give you long flights of about a few months. And if you have sufficient resolution, which we nowadays have up to 30 second sampling, we can resolve theoretically the whole gravity wave spectrum. So what are the observations available, and what observation am I going to show you? Mainly observations from the CNES campaign. So CNES is the French space agency, and over the last decade, they have been launching balloons from the tropics. Some of those last year in 2019, which you see here on the top picture. They were launched from Seychelles and they drifted for 3 months. Making around the world trips. In the tropics, 40 more balloon launches are planned in the framework of the STRATO-TOLE2 project in the next 4 years. We also have observation in the polar region, in the Antarctic polar vortex, with in 2005 and 2010 about 20 balloons launched each time. You see them here, and I'm not going to use those observations, but there are also the Google Loon observations, which are superpressure balloons that were originally launched to provide internet access to remote places, but the program has recently been shut down, but still there were many flights undertaken. So difficulty with this data set, which is very rich, is that there are vertical maneuvers that were performed, and so you sort of partly lose the quasi-Lagrangian advantage that you have with the CNES superpressure balloons. And so what does the spectrum of the motion look like now that you can get rid of Doppler shift by using quasi-Lagrangian observations? This is shown here on the right for the kinetic energy in blue and the potential energy in red. And you see that we find something that is now very similar to what is seen in the ocean at given location. So you have the spectral gap, which is here, and then a near inertial peak, and then the log-log linearity with a slope of here in this data set about minus 1.7. In other data sets, in other campaigns, we get something close to -2. So consistent with a few theories that have been discussed here. And yes, so something that you can check and that gives you confidence that you are indeed probing the intrinsic variability of the flow is the similarity to the oceanic case. Other factors is that those spectra verify the polarization relations. So, for instance, the equipartition between potential energy and kinetic energy in the mid-frequency range, the F peak, which is not reflected also in the potential energy, and another constraint that comes from the gravity wave polarization relation is that the waves induce anticyclonic motions. And if you compute the rotary ratio, which is the ratio of counterclockwise over clockwise motion, it should follow this analytical form. So we have had those observations for years now, since I told you the campaigns are as old as 2005. But what has been changing recently is the increase in the resolution of numerical weather prediction models and the associated analysis. So the initial state that is given to the model with data assimilation in order to perform the forecast. And in particular, the ECMWF, so European Center for Medium Range Weather Forecasts, analysis now have resolution, horizontal resolution, which are close to a few tens of kilometers. And this is a spectral model, so you might expect that they resolve scales of a few hundred kilometers already, and they are available also at high time resolution. And so those models were not designed to represent properly inertial gravity waves. They are designed for weather forecast, but they now should be able to resolve them. And we were interested in seeing whether they are present, the waves are present in those products. And the side question, but this has already been discussed a couple of times, is how to extract these components, inertial gravity wave, from the flow. So related to that last question, I'm going to be very quick here because I think this has been discussed in several talks. The ways that gravity waves have been extracted in atmospheric models from the background flow are so there's a PV inversion method to isolate the balanced flow. There's also the normal mode decomposition using half harmonics, and this has been used to investigate the representation of the Nastrom gauge spectrum in reanalysis. And there's finally intrinsic frequency filtering, which I learned yesterday is in the oceanic community called Lagrangian filtering. And this is based on the property that gravity waves or internal gravity waves can be found between the Coriolis and the Brunt-Väisälä frequency. And so if we filter in a Lagrangian frame, you should find them between F and N. And so how do we proceed to evaluate the representation of the waves in the models? We compute a pseudo balloon trajectory, which we compare with the actual balloon trajectories with a focus on the high frequency or the wave variability. I'm showing here on the left an example of an actual balloon trajectory in gray, and it's the computed trajectory in the reanalysis in red. On the right, you have the vertical coordinates of the two. And you see that the large-scale wind and the large-scale trajectory is pretty well reproduced by the model. So this is already a good start, but what is it? How good is it for the gravity waves? I've picked here a case study or an example of a segment of the balloon trajectory here in green, which during which one balloon was drifting westward, and you can notice on this trajectory that it's not a straight line. You have small cycloids in grid. And if you look at the trajectory that is computed in the ERA 5, so ERA 5 is the last generation reanalysis from ECMWF, and you see that it also shows those nice cycloids. It's even clearer if you look at the time series of the zonal and meridional wind in the balloon observations. You notice, so there's a whole spectrum of waves here, but the dominant waves here have periods of around 2 days, very close to the inertial period at 15 degrees south. And you can see that the U perturbation is leading the meridional wind perturbation in both the observations and the reanalysis. So this is already very convincing that the model is able to reproduce those features. And actually, we sampled those along a few balloon trajectories. You can see them on the bottom left, which shows an Moeller diagram of meridional wind. The time axis is not given, but it's about 2 months here. And you see those more or less a big intermittent, but quite ubiquitous wave packets that we sometimes encounter. So the message here is that the ERA5 reanalysis or the ECMWF model now describes a wealth of waves. And this was for a specific case, but we also performed statistical evaluation using power spectra for all our balloons. And I'm showing here the horizontal kinetic energy spectrum, which so the solid lines are the spectrum and the dashed lines are the rotary ratio, and you have here the analytical estimation. And you see that although quantitatively there's still a way for improvement, there's still room for improvement. Qualitatively, the agreement is pretty good. If you look at the potential energy, you can draw the same conclusion. So here the dashed line are the ratio of kinetic energy over potential energy. And they also both, I mean, the spectral the behavior of the spectrum near the intrinsic frequency and the ratio, which is constrained by the polarization relation, match well the observations in the model. So just for illustration, because as I told you, we have both polar and tropical flights. We can compare basically the behavior of near inertial waves, which are virtually inexistent in the tropics. And you see obviously that the F peak is not reproduced. And also the rotary ratio analysis matches well in both latitude ranges. So now one question, the analysis, as I told you, is a compromise between what the model can do and what the observations feed him through the data assimilation. So one question is what is creating this good behavior? And so we were able to investigate that using two different balloon data sets, one from 2005, which was not assimilated in the model, one from 2010, which was. And the quick message here is that so although the performance of the model without balloon data assimilation is already very good, there's a potential for improvement, which means that the current configuration of the ECMWF model is able to really reproduce gravity wave features.
Aurelian, just a couple more minutes.
Okay, that's fine. And one other parameter to examine is obviously resolution. So I'm showing here different versions of the ECMWF analysis. One is the last generation ERA interim, the new reanalysis ERA5, and the operational model, which have increasing horizontal resolution. And just to show that, as you expect, you feed the high frequencies when you add the increasing resolution. And so I'm now coming to my summary. So although there's a large Doppler shift in the atmosphere, thanks to quasi-Lagrangian observation and superpressure balloon, we are able to resolve the intrinsic frequency spectrum and to find the characteristics that are also found in the ocean and expected from theory. And the current numerical weather prediction models and the associated analysis seems to produce realistic near inertial waves, both statistically and for case studies. We have seen that the higher frequency end of the spectrum is not as well modeled, but that's to be expected. Quantitatively, there's still a large underestimation which can be improved with data assimilation. And finally, so the next steps here, or at least what we plan to do, is to use this relatively good performance of reanalysis in representing near inertial waves to estimate their variability in the atmosphere in the recent period. And so part of what I've presented you can be found in this paper, which was published last year, and the rest is ongoing work. So thank you. I'm happy to take questions now, if I have time.
Okay, we're sort of out of time, but maybe if there's one quick question, anyone? Anything in the YouTube chat? Nidita, I'm not sure how to check that.
There's a raised hand, I think.
Okay, Hussein?
Thank you, Kevin. Yes, very interesting talk. Thank you very much. So the balloons were at a specific height. Do we expect to see this peak near inertia peak at certain heights in the atmosphere, or is,
so I can only answer from, I mean, we only have the balloons. You cannot fly the balloons in the troposphere because of convection. The flights would be much shorter. You can fly them in the stratosphere because there's not so much disturbance. So I can only answer from the modeling side, and from the ERA5, it seems that those waves are clearly more prominent in the upper troposphere and in the stratosphere than in lower levels. So below 10 kilometers, you don't find such a peak, or it's not as clear in the model.
Thank you.
Okay, we should move on to the next talk by Ashrat Klein. Is he here?
Yes.
Or,
yes, thank you, Ashrat. I will share
go
my
ahead.
screen. Yes, I will share my screen. No, sorry. Okay. Thank you. I'm Osrat. I'm a PhD student. I'm part of the marine engineering and physics lab in the Tel Aviv University under the supervision of Dr. Yaron Toledo. This work is on the model of surface gravity waves propagation on viscous shearing currents. This was done with the great contributions of Professor Eyal Hefetz, also from Tel Aviv University. So I'm about to present the model that we worked on. So a little bit motivation about what we've done. So it's important to mention that if we compare to the previous work that I presented here, we're talking about gravity waves. So the scale of the waves is much smaller, and the turbulence that we are add to the models of the waves, it's much stronger effect on the waves. So much work has been done to couple between waves, gravity waves, and shearing currents, and we add here another addition of the viscous to see how it affects the dynamics of the flow of the waves. So a little bit background. So if we start from the governing equations, first, without any viscosity, we start from the Euler equations. So those are the governing equations, the momentum and the continuity. So we're talking about waves with the shearing current. So we have some profile for the current, and our problem is confined between the surface, where z is equal to the water surface, and the bottom. So we have the boundary condition, the dynamic kinematic boundary condition at the surface, and of course the kinematic and the no slip condition at the bottom. So this yields the Rayleigh equation, which is known for the vertical velocity profile. And this is also can be solved as the eigenvalue for the celerity to solve the dispersion relation with the appropriate boundary conditions. Now we add some viscosity. So we're talking about waves with the presence of some turbulence. One unique to our problem is that we're talking about viscosity that changes in depth, meaning that we have some profile for the viscosity. So if we're looking from the waves point of view, it's very reasonable that there is change in the viscosity in the upper layer, which be probably much stronger than in the bottom due to wind or to white capping, the turbulence that causing due to waves. So this problem is already with viscosity and turbulence. So we started with the Reynolds average Navier-Stokes equation. So we added the turbulence, the Reynolds stresses, and the problem is still confined between the surface and the bottom. I will mention here that we took the Buskinesque approximation, so we're talking about incompressible fluid. And one thing that is changed is the dynamic boundary condition, because now the dynamic is a little bit different since we have some shear stresses caused by the turbulence. So since we're talking about waves in the presence of currents, mean flow, we can divide the problem and all the variables in our problem to the known mean flow, which is varying slowly, compared to the waves which varying very short and faster. So the oscillatory terms is our waves dynamics. We took the WKBJ asymptotic approach, even though we here considering only the first order. So substituting this approach in our equation, we got the governing equation. We here already substituted the Doppler frequency, and mathematical manipulation yields the first order ODE equation, which is also known as the Sommerfeld equation. But here we have some additional terms which takes into account the derivatives of the viscosity. This problem also can be solved by the eigenvalue problem, where the eigenfunction is our vertical velocity, and the eigenvalue is the wave celerity. If we sum up, so we have for the 3-dimension case, we have first order the Sommerfeld equation, and this is coupled by the second order ODE for the horizontal velocity. The second order ODE can be written for the vorticity, and this is also known as the Squire equation. But here we also have new viscous terms, which is new compared to the known Squire equation. And for the second dimension case, we have a much simpler form of this horizontal velocity. As to solve and to close the problem, we need the appropriate boundary condition that takes into account the viscosity and the turbulence that affect our solution. So the only condition that changes the dynamic boundary condition on the surface. Now we have Reynolds stresses. It affects somehow on the waves. So here we present the force balance on the surface. So since we're talking about waves, we have the tangential direction and the normal direction. And we took the known relationship between stresses and vertical gradient, and here we present the wholesome dynamic boundary condition. We wrote here that it's equal in the right-hand side of the equation to some stresses. This could be stress caused by the wind or something else, but here in our solution, we consider this for the unforced case. So sigma 1, sigma 2, and sigma 3 in our case is 0. And also for the boundary condition, we took the WKBJ approach, and here is the problem with the coupled governing equation. So we have fourth order ODE for the vertical velocity and second order ODE for the horizontal velocity with the appropriate boundary condition at the surface and on the bottom. And for the second dimension case, which is much simpler, we have only the fourth order, which is the Orr-Sommerfeld type equation with the appropriate boundary condition. So this is the model that we created, and I would like to present now a few examples that we have. So started with very simple, simpler case. We talked about a constant current without any shear, without any profile in the vertical direction, and constant eddy viscosity. So we reduce the Orr-Sommerfeld equation into a form we have when we don't have any derivatives in the z direction for the current and as well as for the eddy viscosity. So good thing is that we do have analytical solution for this case for the vertical velocity. For the eigenvalue, for the celerity, we do solve it numerically. So it's important here to mention one comment about the eddy viscosity values. So as we know, there is no field measurements of the eddy viscosity value that we are interested in. Most of the field measurement that we found was for the dissipation factor. We did find one research from 1936 that measured the eddy viscosity in rivers. So they found two main results. One is that the profile of the viscosity might be a little bit with changes, but it can be some constant in some depth. So if you compare it to ocean, we can assume that in the upper layer we're talking about constant viscosity. And another result is the values that they measured. So they measured values of viscosity that are much greater than the molecular viscosity, and they reach to values that are around 1 or 0.1 viscosity. We assume that for extreme events like hurricanes or white cappings in the ocean, we could get the same values. So our examples are for viscosity of 0.1 meters squared per second. And here is the first result. So the dispersion relation, in the first row, we can see the dispersion relation for different values of viscosity. We can see that the bigger or the stronger the viscosity is, the dispersion relation gets actually smaller values of celerity. But what is interesting is if we're looking on a specific viscosity of 0.1, we can divide the results into two zones. Zone 1 is for the shorter waves, and we can see that we found solution for 1 wave celerity, and this wave celerity is equal to the current that we checked. And in this zone, we found one solution for the wave celerity, where if we compare it to the imaginary part of the celerity, we found a bifurcation of the celerity. I will explain a little bit this figure. So the imaginary part of the celerity, of the phase celerity, meaning the decay of the waves. So we can see here two branches, which one is much stronger, and in fact we found many more modes, but most of them are not physical because they're meaning that the wave decay very shortly. And if we see the zone 2, so we see zone 2 is with the same wave celerity of the image part, but in the real part of the wave celerity, we see the bifurcation of two branches, where both of them are smaller than the potential solution. So the black line is the potential solution because here we talked about constant current without any shear. And moving on to second. Sorry. Here we present the vertical velocity, which is the eigenfunction of the problem. We can see here that in zone 1, which is for the shorter waves, we get two very different profiles. Here we normalize the two profiles to 1 in the surface. So the amplitude is different, but the profiles are very different than the potentials. We can see here that the wave celerity for the real part is the same, but the imaginary part is different. And as for zone 2, which is for the longer waves, we see that both of the profiles are united with the same profile, but we get two different values for the wave celerity. Both of them are smaller than the potential. I will present shortly a solution for shearing current. So we took, for this example, profile of exponential value for the current. We still considering the eddy viscosity as constant. So the Orr-Sommerfeld equation reduces to this form. For shearing current, we don't have any analytical solution. So I will present our interesting results. It is important to say that we got these results also for the constant current and even for no current at all. So here we present the stream function. The upper row presents zone 1, which is for the shorter waves. We see here two branches of wave imaginary celerity. I will zoom in a little bit. So this is for no turbulent. This is actually solving the Rayleigh equation. Here we can see branch 1 and branch 2. We can see that the penetration depth it's much larger than the solution of the Rayleigh with no turbulent. But the values here are much different. So for branch 1, which is decay slower, we have the same values as the Rayleigh, and for the branch 2 we have much smaller values, but penetration depth bigger. What is interesting is actually zone 2, when we see two branches of the dispersion relation, and we can see in the stream function the tilt. So usually when we see this tilt in the stream function, it says something about the instability, but here we're talking about stable case. So meaning that the viscosity caused this, only the viscosity caused this tilt. And this work is still in progress, so this is the results we got. We're still working on the physical explanations. My time is up, so I will conclude that we added the viscosity term to our problem of waves in the presence of shearing currents. We see that the viscosity cause changes in the dynamics. The work is still ongoing, so our conclusions are still in progress. This work can easily be extended to internal waves. So we would like to hear your comments or inputs on our results. And thank you very much.
Okay, thank you. So time for 1 or 2 questions. Anyone? Okay, well, I had one question, or a couple of questions. So the turbulence that you're modeling with this eddy viscosity, it's due to the background current, background shear current, so nothing to do with wave breaking. And then I was also wondering whether the eddy viscosity should be non-isotropic, say different in the horizontal and vertical, or different in the, say, a long wave and cross wave directions.
So for the first question, we also found some research that found that eddy viscosity exists even without breaking. So even in deep water, there is a viscosity that can change the dynamic even without breaking. So it's not only for the breaking zone or near shore. It can happen even for the deep water. And for the second, we assume that the scales of the viscosity is the same for the vertical and the horizontal directions.
Yeah.
So we're talking about very. Sorry.
Are there measurements that would justify that assumption?
Unfortunately, we haven't found any field measurement in the oceans to see what is the real values, but we found only this research for rivers, which is also from 1930. So
hey, thank you. So
maybe
sorry,
I can.
did I hurt someone?
Yeah, maybe I can add for the answer, Kevin. The scales are very small, so we don't expect the vertical to be different than the horizontal. We are not blocked by the bottom or something like this. These are very short waves. So we expect it to be more or less the same, but it can change and it can be incorporated inside. But we don't have better information, as Efrat said.
Okay, thank you. So let's move on to the next talk and the last talk of the day. It's by Laura Zana. So.
Thank you very much, everyone, for sticking around. Yeah, perfect. Excellent. Hopefully you should see my screen.
Yeah.
Yes?
Yep.
Okay, great. Yeah, so thank you very much, everybody, for staying, especially if you are somewhere in Europe. It's getting probably pretty late, so it's greatly appreciated. And thank you again for the workshop. It's been phenomenal so far. I've learned a lot, so it's been very interesting for me. So what I thought was, given the fact that unfortunately many of our researchers in the climate process team could not present at this event for various reasons, I thought that I'll try to give you an overview of what the work has been in the last few months since they've started, what our goals are in the climate process team on ocean transport and eddy energy, and where we're going. And the reason for that is also to try to create connections, between us, because again, both projects are very much involved with energy transfers and how to improve climate models and how to understand those processes better. So I hope giving you a little bit of an overview of the project, the goals, where we're at and where we're going, will help actually cement those collaboration and hopefully get some discussions going, across the Atlantic, I guess. So as you can see, there are many names here, so many people are involved. in this project at many institutions, but I really want to flag our early career researchers, so Nirja Bamidipati, Noah Luce, Gustavo Marquez, Jake Steinberg, and Elizabeth Yadkowski, who've kind of really started in the last few months, have done amazing work as part of this project, working with many of us. And so this is the entire team for one of our project meeting. So, they get all the credit and I get the blame if I say something wrong. But also, many colleagues across many institutions that are, advising those early career and really kind of contributing through the project from beginning to end. Okay, so I'll start with something that probably many of you on the ocean side are quite familiar with, which is basically the energy cycle in the ocean and the role of mesoscale eddies. So we know that we have basically input of energy at the large scale from wind and buoyancy work that really drives the large scale circulation on 100,000 kilometer scale. This basically sets the large scale available potential energy reservoir, and that energy basically cascade towards smaller scale, where the mesoscale, which are again horizontal scale for about 10 to 100 kilometer, roughly sits at the deformation scale, are there to actually extract that energy from the available potential energy reservoir and transfer it into the kinetic energy reservoir, which was mentioned earlier today by Stefan. And so this is done via volcanic instability, where again, at the formation scale, the eddies are extracting that available potential energy and moving it to the kinetic energy. Now, of course, as they're transferred into the kinetic energy, some of that energy is being backscattered. So basically it's being moved towards the larger scale while some of it is being dissipated. So you can see that the mesoscale eddies are really kind of sitting at this crucial boundary here by extracting available potential energy, moving it into kinetic energy, and again, setting up the large scale flow overall. So understanding those transfer of energies is really critical for understanding how the ocean works, but also parameterizing them in climate model is critical. And, symptom of missing energy in general circulation model is, plots that we've seen many times. So here is surface kinetic energy at 3 different resolutions. So this is a 1 degree ocean model. This is a 1/4 of a degree, and this is 1/12 of a degree. And of course, what you can see is that there is more kinetic energy as you move towards higher resolution, right? So the flow is more turbulent, and you expect that you're resolving more mesoscales, you get more kinetic energy, what is more variability in the kinetic energy. But what's important as well is if we look at the fluxes of available potential energy to kinetic energy, or what we call again the backscatter, this kind of energy transfer from small scale to large scale, which is illustrated here. So we're looking at a flux as a function of wave number for the 3 different resolutions that we've been looking at. So this is the high resolution in green, and we're looking at the backscatter. So the transfer of energy from the small scale, so where it's negative, to the large scale where it's become positive. So you're literally fluxing energy from small scale to large scale. And this is happening at high resolution. When you're at 30 degree resolution, so you're kind of, letting some eddies, being around, but not all, you can see that backscatter or that inverse cascade is actually a lot smaller. Still present, but much smaller. If you're at 1 degree, obviously you have a flat line. None of that is happening. And so again, part of those, weak or inexistent fluxes and the lack of mesoscale eddy is basically giving rise to some biases in the transport. And so here's an example of depth versus latitude of transport in general circulation model. So we're looking at velocity in the Korea region. And as you can see, and as you can expect, right, so you basically have a very weak current, but also the vertical structure of the current is very different from 1 degree as you move towards higher resolution, where in some places it becomes a lot more barotropic. So again, this kind of lack of fluxes in energetic give rise to biases in ocean transport in climate models. So the aim of our climate process team is to actually increase the fidelity of the large scale transport in IPCC class models. So we're really looking at global climate models here by unifying the energetics, so basically the energy transfers and the current and hopefully future eddy closures of momentum and buoyancy. And we're targeting parameterization that will be resolution aware meaning something that you can use across different resolution. Scale aware, again, the flow can be different in a sense, and something that can really capture this transfer of energy between available potential energy reservoir, kinetic energy reservoir, but also across scale. So this is really critical for parameterization that can be implemented in a range of models at different resolution for them to be successful. So the objectives here are, one, we need to evaluate existing and future parameterization. So to do that, we started with an idealized configuration that I will present in a minute called Neverworld 2. And it's going to be our test bed for all parameterization, diagnostic of energetics, and so on and so forth. Before moving, of course, to global models, which is our target. And so here illustrated with the NCAR global model. The second objective is to unify closures of momentum and buoyancy through the energy pathways. So again, the first kind of picture that I showed you really gives you an idea already of how we move from available potential energy into kinetic energy and so on and so forth. So having the right parameterization, both in buoyancy and the momentum equation, to actually mimic those transfers and mimic those pathways is going to be critical. So I'll show some results from Neverworld 2 on that and where we're at. And finally, we are aiming to curate observational diagnostics so that we can evaluate models. So in the idealized world, you can always run simulations at high resolution, so you always have a truth to compare against. When you go to a global model, that's harder, right? So you can't rerun many experiments and try to do those diagnostics. But we have observational data, and so I'll show some example on how to come up with scale-aware parameterization, scale-aware evaluation of different aspects of the energy pathways that we're trying to capture in the model. So as I said, the critical thing you want to remember probably here is that everything has been done by our early career scientists. So Neil, Jan, Nora, Gustavo, Elizabeth, and Jack, they really kind of spearheaded a lot of the results I'm showing here. So they get all the credits. Okay, so let's start with the first objective, which is basically evaluating existing and future parameterization. So this morning, Stefan mentioned backscatter, but there are many parameterization out there. So David Marshall and Alistair Adcroft kind of started with some of those, eddy energy prognostic equation in two-dimensional. Karsten has a three-dimensional parameterization. We have some backscatters. We have geometric from David Marshall and Julian Mack and colleagues. So there are quite a few out there. And many of them improve the flow under certain circumstances, but there are a lot of tuning parameters, as we heard this morning from Stefan. Depending on what you do, you can either improve your simulation or you can degrade it. And the question is, of course, is what did it do right and what is wrong in those parameterizations? So actually we had the right answer for the right reason. And so the idea will be to actually use a very simple setup. And so this is Neverworld 2 that's been set up at GFDL using MOM6 code, and something that is simple enough that we can run many experiments, that we have a truth where we can evaluate all the fluxes that we wish. So here's the setup. This is the ocean depth. We have a continental shelf going around. We have a re-entering channel in the Southern Ocean. We have a very large topography in the middle of the basin. And so this is the continental shelf, by the way. And we have a ridge that blocks the re-entering channel. It's forced with wind only, so very idealized wind profile, and has 15 vertical layers. So it's basically a stacked shallow water. So this is the density profile for our layers. It's adiabatic right now. There's no buoyancy forcing. We might revisit that later, but for now, it's actually a very simple setup that, again, is affordable, where we can run very high resolution and do extensive analysis and diagnostics with. Now, the reason that the model was set up also in MOM6 is MOM6 is the base code for both the NCAR and the GFDL model, global models. And it's also basically open development and open source. So you can go on GitHub and you can see everything that is happening. And of course, it's been used already as part of OM4 and CM4, which are couple climate models. And it's going to be basically the ocean component of the next NCAR CESM model, where you can see already the first step towards implementation that's been done at NCAR, which again are already include some new schemes for mesoscalities. So really kind of having this model in MOM6, even though idealized to start with, is just a stepping stone until we actually can move towards global models. Okay, so as I say, it's stat shallow water. So here are the equations that you're all familiar with. It's just to show you a little bit of an idea. And of course, we're going to concentrate a lot on the kinetic energy budget and the eddy kinetic energy as we move forward. So this is our truth. So we have two truths, actually, 1/16 of a degree and 1/32 of a degree. So here we're looking at surface properties. So we're looking at non-dimensional relative vorticity. So again, a few places where you can see nice filaments and some eddies, in various places of the ocean. So really the high resolution gave us some kind of nice structures and instabilities. If we look at the vertically integrated kinetic energy, again, you can see a lot of turbulence in the Southern Ocean, in the re-entering channel. Tropics are also very turbulent in our western boundary extension as well. So the flow is very eddying, and again, kind of, hopefully mimic the right energy transfer and the right pathways, or at least this is our truth for our experiments. So the way we're going to use those simulations are twofold. The first one is doing a lot of offline analysis using the high resolution data, right? So the high resolution is our truth. This is what we're aiming for. And so what we can do is we can filter those high resolution simulation to test offline the parameterization or the optimization of the parameters that we expect to have in a given set of parameterization. So here is just kind of an experiment to show, you can diagnose the fluxes, the eddy fluxes from the simulation and try to estimate what would be the Gent-McWilliams coefficient that would actually fit those fluxes, assuming the GM parameterization is correct. And so that's one simple way to actually use the data, try to understand, what will be the optimal parameter setup that we're looking for. And I'll show an example of a different way to do an offline analysis in a bit. Second reason, as I say, is to actually do online evaluation, right? So we actually take the model at high resolution. We can look at its field. So over here, this is a stratification at the 1/32 of a degree. And then we take exactly the same model on a coarser resolution, so half a degree. And we assume that Gent-McWilliams is the correct parameterization. We implement it with a given coefficient. And of course, as you can guess, we're getting large biases. And again, some of them are occurring near topography, the largest one, probably due to standing eddies. We also get very large biases in the interior. So those online evaluations are a way to actually take all those parameterizations that have been put forward in the past and are currently, being advocated for by many of our members in the CPT, myself included, and really, test them properly in a way where we actually can diagnose what they do right and what they do wrong and why. Really, the why is the most important part here. So, I talked about GM over here, and so GM has been really kind of a revolution in ocean models, right? It's been a phenomenal parameterization to avoid, having spurious mixing everywhere in the ocean, a good representation of volcanic instability, but it's a net sink of available potential energy. So the question is there a way to actually keep track of that eddy energy using a prognostic equation? So again, Stefan mentioned that earlier this morning. So one way to do that is with a 2D depth average mesoscale eddy kinetic energy, so which I refer to as MIKI. And all it is basically a prognostic equation that keeps track of the eddy energy being equal to sources, sinks, and some transport. So again, Carsten has also, a long time ago postulated for a prognostic eddy energy equation, but using a 3-dimensional equation. So here we're kind of only looking at a 2D version of it. And so again, one way to actually use that eddy energy equation could be to actually scale the Gent-McWilliams coefficient, and that's been done already at GFDL, or to actually ensure that the energy is being conserved in a pathway. So again, David Marshall of Geometric kind of does a combination of both, and I'll talk about some of the work relating to backscatter from Malte Jensen and others as well in a little bit. So you can have basically a reservoir of resolved potential energy going into kinetic energy and then being fed into your subgrid eddy kinetic energy that actually keeps track of all the different parameterization sources and sinks, and has again its own parameterization as well within it. But at least you can keep track of those different budgets. So of course, now again, everything that you introduce in a model as a way to keep track of the parameterization will have its own parameters and its own parameterization. And so the question is, how do we evaluate that this is correct too? And so again, this is what we're doing offline. So here is, again, what we call Mickey. So it's this kind of, parameterized version of the subgrid eddy kinetic energy. And so you can see a source coming from Gent McWilliams, and basically other bits and pieces. So some of them are, again, sources, others are sinks. So the sinks dissipation, but you can also have basically the backscatter that will reintroduce the energy being lost, which again, Stefan mentioned this morning. And so understanding the pathways between the different reservoirs is something that we can do directly with our high resolution simulation. As I said, we take the output of the high resolution, we can filter it. So here we've been using thickness weighted averaging for the filtering. And we're filtering from a given resolution, which is here in this case, 1/16 of a degree to 1 degree. So just to give you an idea, we're doing it for different resolution, obviously, to understand the behavior of the eddy kinetic energy budget. This is what the field looked like. So that would be the total kinetic energy. This is the mean kinetic energy, and this is the eddy kinetic energy, given that filtering operator. Note that our definition of eddy kinetic energy and the way we define the subgrid is really as a spatial filter, not a Reynolds time averaging that some of you are familiar with. And in addition, the eddy kinetic energy in our budgets are conserved, meaning that if I sum the mean, over here and the eddy kinetic energy, I actually recover the total kinetic energy in the model. So that's the way we're doing the diagnostics. And so, as I said, we're in a model where we have all the diagnostics we possibly wish, and so we can actually decompose the different terms in a budget and understand how the pathways between different reservoirs. So in this case, you can see, for example, this term over here, which is the transport of eddy kinetic energy in the Southern Ocean that seems to be actually rather strong. So a lot of transport in that region of the ocean. And so this, this kind of calibration, this kind of estimates of the different term in the eddy energy budget diagnosed from the high resolution simulation really help us understand how accurate is this to the eddy energy budget is. How would we ensure the fidelity in the kinetic energy pathways we're looking for, and how to actually best optimize the parameters that we have both in the eddy kinetic energy budget and the different parameterization that are included in the model in the buoyancy or the momentum equation. So this is kind of the glue between the different parts of the model, and being able to assess those pathways is critical. So for us, again, the idea is not to get just the right answer in terms of reducing biases, but actually improving the fidelity of the model when we're thinking about those different pathways between different energy reservoirs. Okay, I also mentioned that one aspect that was critical for us was also to have a parameterization that is scale aware, meaning that we can understand, or at least implemented in a different range of models at different resolution. So what we have, again, because we have a very idealized model, it's pretty easy to run it at many resolutions, many different resolutions. So our truth cases over here, basically, we assume, again, based on our definition, that they resolve eddies. And when I say resolve, it's because we're actually using the deformation scale over the resolution and using, again, the criteria nicely set up by Bob Bagberg, but also long before, but kind of nicely laid out in Bob's paper. Here in our idealized simulation, we can see that, again, based on that criteria of deformation scale over the horizontal resolution being 2, so basically resolve 2 times this number. So the 1/16th of a degree and the 1/32nd of a degree are basically eddy resolving, so they are truth. For lower resolution model, which are kind of equivalent to the current generation of ocean or climate models, so then we can see that in many places we do not resolve eddies. So the question is, without parameterization, and of course, if we were adding something at 1 degree, nothing will be resolved pretty much. So the question is, would our parameterization work as well at 1 degree, 1/4 of a degree, or 1/8 of a degree? And what are the pathways that we really need to improve? And I want to mention that there are similar efforts going on at Los Alamos, who are also involved in our climate process team with unstructured grids. And I think that relates with, again, some of the work that you are doing in this project. For example, again, Stefan mentioned that this morning. So I hope, again, with all those slides, you actually can see some connections across different groups and across different themes. Okay, so for scale-aware and scale-aware unification, so I'm going back to something that I mentioned early on. There are new schemes that try to actually re-inject the energy being removed by Gent-McWilliams into the resolved scale in the momentum equation, mostly using anti-viscosity. And so again, going back to what Stefan mentioned. So two examples here, one from Scott Bachman, another one from Malte Jensen. In both instances, again, the flow and the kinetic energy is actually improved by using this backscatter, very similar to what Stefan mentioned this morning. Both of them use, anti-viscosity. The question is, is it the right form? How to re-inject it? Again, should I have a vertical profile? What would that profile look like? And how do you set it up? There are other flavors of energy backscatter schemes that do not use anti-viscosity, that have dependencies on the local flow, for example. So a couple of them are here. Some of them are derived from physics. This one is derived from machine learning, equation discovery from machine learning. So there are several flavors out there, not just anti-viscosity. The question again is, what would be the parameterization that remains true to the flow and that can adapt to different resolutions? So really how to energize the flow in a physics-aware and scale-aware way. So I'm looking at the clock. I think I'm running out of time, so I'll just skip that one and just show two final slides. So if we look at it as a function of resolution in terms of what's happening in the energy transfer, and again, how that backscatter may occur. So here is a set of the fraction of kinetic energy separated between barotropic and baroclinic modes. So fraction is over here as a function of latitude. So this is the zonally integrated picture. So we can just concentrate on the yellow curve over here. And we're going from 1/4 of a degree at the top, 1/8 of a degree in the middle, 1/16 of a degree at the bottom. So if we just concentrate on the yellow curve over here, so what we can see is that the flow is becoming more barotropic. So there is a barotropization as we increase resolution in our simulation. So again, as the eddies are resolved, more momentum is actually being transferred downward, creating a flow that is more uniform with depth. And so again, this is part of that energy pathways from available potential energy into the kinetic energy, which is really kind of mimicking this baroclinic to barotropic transfer of energy. So the question is, how does one parameterize that, as a function of resolution? What would be the best way, again, to either improve on the backscatter or to create a different set of parameterization that can actually mimic the barotropization of the flow, that can scale with resolution, or at least that can capture this effect as a function of resolution. So finally, so I've shown you everything in the very idealized world of Never World 2. But of course, we're going to move towards global simulations, and we have observation, which is the real world, right? This is what we're trying to mimic at the end of the day. So this is really exciting. This is really exciting work by the ARMS team. So what they've done is trying to estimate what is, basically a scale-aware evaluation using altimetry data from global data sets, right? So basically, they calculate eddy kinetic energy using the same filtering approach that I mentioned, so kind of a very simple spatial filter. They've done a lot of sensitivity actually to the shape and size. And what you can see is actually the seasonality and its geographical distribution as a function of resolution. So basically filtering across different scales. So we're going from 70 here to 270 down here. And so we can see the increase in resolution. So what you can see again is basically, less energetic summer, right, on kind of small scale. And this gives us a way to really evaluate the energy as a function of resolution, or as a function of scale, if you wish, when we can go to global simulation, but also a possibility to actually constrain our parameterization down the line when we think about Mickey, for example. So this is kind of a first step towards global evaluation. Okay, so as I said, I just wanted to give you a brief overview of what we've been doing in the last few months. And as I said, again, our early career researcher, I've done all the work are really driving the effort. So it's the very beginning, and we're moving forward with both the evaluation and idealized simulation, but also hoping to actually implement many of those parameterization global models as well very quickly, and trying to be faithful to the energetics and its pathways as a function of resolution and as a function of scale. You can find a lot more details about all the aspects that I mentioned. So if you go on YouTube and you Google and you basically type 2021 CESM Ocean Modeling Meeting, so all the aspects that I told you about right now have each one 20-minute full talks where you can go through the details and the results and a lot more in there. So thank you very much. I'll leave it there.
Okay, thank you. Questions? So Stefan?
Yes, thanks, Laura. That was very interesting, and I think that's pretty obvious that there's quite a lot of common interests in these topics. I think we are going in very similar ways with a lot of these things, so it would be really nice to
I love it. Yeah,
collaborate.
that's great. That's very exciting.
Yeah. The one question I had with regards to, I mean, you're mostly using, you said you also you have collaborations with an unstructured dynamical core. The one thing I was wondering is, with all these diagnostics that you're doing, do you also specifically focus? I mean, that's the thing that at least I saw. One of the troubles I had was with numerical stability, obviously, right? So, and that very much, I think, also with talking to the NEMO community here in Europe, depending on what type of mesh discretization you use, whether it's A-grid, B-grid, unstructured, structured, and so forth, you get very different problems and very different issues with all these parameterization approaches.
Yeah, so I think that's an excellent question. So, so Los Alamos is kind of starting up. They've started by first kind of reproducing our configuration at high resolution, on month 6. So it's pretty exciting. So that means that now we have two setups. They haven't implemented yet new schemes, right? So right now they, so basically Alice Bartel is kind of spinning that up. So she's starting with kind of setting up a truth first, then doing some diagnostics. But yes, I think I'm sure they will probably struggle with exactly what you're saying. Not that we're not struggling as well, right? Even in our regular, the way I call it, regular models. I mean, as you said, right? As soon as you do something like backscatter, things can get pretty tricky.
Thanks.
Karsten?
Yeah, I have a question about your truth. I understood that this base model which you're using, this idealized model, is a adiabatic model. That means shallow water or layered model, isopycnal model with without any mixing. What happens if I speculate that the mesoscale eddy sink, eddy energy sink, is convective overturning and symmetric instability, as similar what we saw this morning in the talk by Fraser? What happens then if, because you cannot have this in the shallow water model, and then the energy cycle of your eddies is screwed, and then the eddy or your truth would be wrong, right? Or what would you do?
Yeah, so that's an excellent point, and so that's what I mentioned, right? So it's adiabatic for now. We are thinking about adding, or thinking about mixed layers, for example, as a way to rethink the interactions. But it's true, the sink of eddy energy in our cases will not be through submesoscale or such symmetric instabilities. So that's true. Our truth might be biased, but again, we need a stepping stone towards something more realistic, and I believe this setup as a first step, towards a true evaluation, at least of the current parameterization, is an important one because it hasn't been done before. So at least from in terms of the large scale backscatter and transfer of APE to KE, I think it's a very good setup, but as limitation, as you said, when it comes to dissipation.
Can I ask a second question?
Sure.
You're in charge, right? I can't see who's there.
In this slide, you talk about unifying energetics and unifying parameterization framework or something. Is the aim actually to have at the end a single eddy parameterization, one which fits everything, or which fits all? Or do you want to still keep this variety of different parameterizations?
So we're thinking. So for us, unification is basically the link between momentum, buoyancy, and energy, right? So this is the one part that we believe should be unified, in the sense that again, those different parameterization are not disconnected from one another when we think about the mesoscales. Then the second, and I guess the second part of your question is, should it work for everything? So it should work for the mesoscale range, not for all processes. But the idea would be to have something that scale with your flow or your resolution, meaning that again, something that as you move towards higher resolution or lower resolution will scale, say, with the deformation or with another non-dimensional number that actually fits the flow regime that you're in.
Okay, maybe the last question then from Marcel.
Yeah, so I know you have played with learning subgrid models or learning the parameters of subgrid models, and you're also advocating to have models that are scale aware or at least work through a whole range of scales. How does that fit together?
Yes, that's a very good question. All right. So when you say learn, I believe you're referring to machine learning work that I've done. Yes. So we've done a lot of machine learning eddy parameterization. Some of them that are directly learning from features with deep learning, where we have no idea what the output is. We have thousands of parameters, if you wish, and we don't know what the structure of the model look like. And others where we actually learn equations for the subgrid parameterization. So we discover an equation for the subgrid. So I think in both instances, I actually do think they fit together in the sense that, so with the machine learning aspect, we're actually learning across different resolution to actually try to have a parameterization that will scale with different resolution, or at least that will adapt to different resolution. And the problem with machine learning is, of course, if you go to too coarse, then you learn nothing because you have no more features to learn from. So I think for the machine learning aspect, it only applies when you're in the eddy permitting regime. So I think that's where I see. I don't see them being disconnected, but I see them only being over a certain range, which will be eddying.
Okay, it's very interesting. Thank you.
I might be wrong. We'll see as we move forward.
Mm-hmm.
Okay, I think we should stop here. I'd like to thank all the speakers today. I found it was a really interesting day, and pass it over to whoever's looking after the photos. I'm not sure how this is going to work.
Yeah, I think there were two more questions, and since we are already in the discussion time, we may quickly address them, and then we can do the photo. So I think Remy had a question.
Okay.
Also Jinsong or something in the chat.
Back.
Hi, thank you, Laura. Hi.
Hi, me.
The first question was about, in your talk, you talk about energetics and consistency, and there were sometimes you talk about potential energy, sometimes eddy potential energy, and I've been trying to push for the use of a budget of eddy available potential energy, but there seems to be a big reluctance in the community about even talking about or defining eddy APE, and I never see anybody attempting to construct a budget except in the atmosphere. And the oceanographer seems to be, Malte Jansen don't even put a box for the eddy potential energy. So is there something that you are considering or thinking about?
Yes, we are. And I think it was in one of the boxes that I showed. So this is something we're thinking about, and actually something we're discussing also actively. And I mean, yes, your paper is one of them that was raised, that came out recently, but also there are different observational estimates as well that are actually trying to think about the available potential energy budget. So we've been talking about this. I don't have a final answer for you, but it's surely something we're talking about and thinking about.
Because in the atmosphere,
so it'd be great to talk. Yeah, I know. For the atmosphere, it's a different setup as well.
It has been realized that that it seems to be important to kind of instead of using a mixing efficiency, using a turbulent kinetic energy budget, predicting the viscous dissipation and predicting mixing from using a mixing efficiency, you can directly compute the AP dissipation from your AP budget. And people think that having the two budget is quite important to develop parametrizations. My second question was about, I was interested about your increased biotropisation with increasing resolution. And I was wondering whether it was dependent on the regional location. For instance, that because it seems that in the Western boundary current, it's more barotropic than elsewhere. Is that what you observe as well?
That's a great question. Actually, it's definitely regionally dependent. Actually, our southern ocean is rather barotropic to start with. So barotropisation is actually smaller there because again, you're starting barotropic. In the Western boundary current and the jet extension, the barotropisation there definitely gets stronger. So we're analyzing all of this and trying to understand again the regional dependence on the flow. But yeah, it's a good point.
Thank you.
Thanks.
So now you want to ask your question?
Actually, just following up to Remy's comment, I guess you do need a kind of definition for the available potential energy, which is local rather than global. And yeah, in that sense, I guess you need to move in that direction.
That's an excellent point, and very deep discussions we had. So we're basically looking at it in terms of a column, right? So this column integrated local AP budget. So yes, that's why it's a long discussion, right? Because it's not simple.
Yeah. The other thing is you have the zone of your parameterization. How about the stochastic parameterization? I don't mean about the uncertainty in the parameter. I mean that we see that if we do resolve eddies, we have variability of eddy buoyancy fluxes, which is order of magnitude larger than the mean eddy buoyancy flux. So this is something really physical features. What are you going to do about them?
Yes, and great question. I mean, as you know, many of us, in the client process team are definitely very involved in stochastic parameterization and your work as well, of course. So right now there is right now we're not going towards the stochastic parameterization to start with. Not that we want, right? I mean, obviously. So, for example, we started looking at a seasonal cycle, at least in the observation. So this is something we're thinking about as well. As you said, the variability can be as large as the mean. So this is a component that we'll need to think about. The question, will it be stochastic or will it be, something different? But yes, I mean, as you know, I'm a big fan of probabilities when it comes to thinking about the variance around the mean. So,
Okay, I think people are slowly disappearing from Zoom, so we should just take the photo. So if everyone is willing to turn on their camera, we can attempt this online photo shoot. Is the second photographer, where is he? Okay. All right, so it takes a while because everyone doesn't fit on the screen at once. So try to hold your smile a little longer. Okay, you may start smiling now. And keep smiling until we tell you to stop.
I cannot hold any longer.
You'll have to cast or you'll have a bad picture.
I made about a dozen. I think if you made another dozen, I think we are fine.
Yeah, I think I have now everyone, but some people didn't turn off their camera. So, but their names are there, so they are present. That's good.
It's like taking a picture in the 19th century, right? You have to freeze for 2 minutes.
Yeah.
We can also ask everyone to send their picture, then we integrate it together and send it back to you. But yeah, thank you everyone for staying until the end. For all the speakers today, again, who woke up early this morning and who might be already late at the places. and all the session shares, and all the listeners on Zoom and YouTube. Thank you for interaction and contribution and all the discussion. It has been great so far, and we look forward to meeting you again tomorrow because we have another set of exciting talks waiting tomorrow. Have a nice evening. Don't forget there's still Gather Town. I will put the link again in the chat so we can meet some of you there. Have a nice evening. Bye-bye.
Bye. Tschüss. Bye-bye.